Hello everyone and welcome for this short course about superconducting electronics. I'm Pascal Febvre from University Savoie-Mont-Blanc in France, and I'm going to make this course by starting really from an overview and going to the detail of superconductivity, then Josephson junction, then application based on this device. So this is the first part, which is about an overview first of superconductivity, starting with a history, in fact, of the discovery of superconductivity. Basically, superconductivity has been discovered in 1911, a bit more than 1 century ago, by Kamerlingh once in Leiden, when he was doing with his students some experiment about mercury that has been cooled down to 4.2 Kelvin. It was a temperature possible when helium was liquefied, which has been liquefied for the first time by Kamerlingh once. So he was the only one to be able to do this kind of measurements, and he has a very big surprise to observe that the resistance of mercury went down to zero immediately at 4.2 K. So that was not understood at this time, of course, and there were, but still it was a repeatable experiment, and then that was the first, the beginning of the story of superconductivity. A bit later, 20 years later, nearly, other properties have been found on superconductors, and have been shown by Messner and Oxenfeld. And they observed that when you apply an external magnetic field on a superconductor material, then as soon as it becomes superconductor below a certain temperature, which we call the critical temperature, the magnetic field is totally expelled from the metal. Now, it's like a perfect diamagnetism. It's not exactly diamagnetism, but it has the same properties, than, meaning that there is no magnetic field at all inside the superconductors, and it led to one of the most impressive experiments with superconductivity, which is the levitation of superconductors or in front of in presence of magnetic field, so close to a magnet, as you can see on the picture below here. So that was at this time observations, mostly observation, but without much understanding. The first people who tried to understand superconductivity were the London brothers, Fritz and Heinz London, in 1935, and they really tried to find the electromagnetism and the electrodynamics of superconductors. So they published the equations, and there is a very nice book, in fact, that you can see on this slide. It shows superfluids, macroscopic theory of superconductivity. At this time it was $1.45, but I think it's, I don't know if you can still find it easily now, but probably not for this price. Anyway, it's a very interesting book. It's written a bit in the same way as the Feynman books on the Feynman lectures, so it's made in it's very pleasant to read. It's not just equations and physics, it's also stories and explanation with common sense. So that was for the, I would say, phenomenological approach of superconductivity by observing global properties and trying to model them in a macroscopic way. This work has also been done in Russia, mostly by Ginzburg and Landau, and in 1950, they succeeded to develop a theory to explain the macroscopic properties of superconductors. And from this theory, which is a phase transition theory, I would say that they've been able to understand the existence of two types of superconductors, type 1 and type 2. In type 2 superconductors, the magnetic field penetrates in a, let's say, not in a fast way, but progressively with some vertices which appears, and you can see a picture which has been obtained years after, which shows some order, right? Some you can see some vortices, some vortex of magnetic field in this superconductor. So when it's totally superconductor, there is no magnetic field. Then you have these vortices when you apply a higher magnetic field, or if you increase the temperature in presence of magnetic field. And little by little, when you increase the magnetic field, then the superconductivity totally disappears. So this kind of theory has been also developed after with Pierre-Gilles de Gennes in the Collège de France, who tried to understand superconductivity as a phase transition with a phase transition theory, as liquid crystals or other material transitions. So it's a phenomenological theory, so it doesn't give us any information about how it is inside at microscopic scale, but it's quite helpful to understand a lot of things. And another point, peculiarity of this theory, it's usually quite accurate, close to TC, close to the transition phase, to the critical temperature, but not at all temperatures. But then a bit later, there has been a microscopic theory which has been developed by Bardeen, Cooper, and Schrieffer in the United States. In '57, in fact, they succeeded to understand really at a microscopic scale what was superconductivity, and that for this they obtained a Nobel Prize in 1972 for this theory, which is called the BCS theory, Bardeen, Cooper, Schrieffer, from the initials of their names. So that's not a simple theory, and I'd like to mention here, and maybe to emphasize that between the discovery of superconductivity and understanding of superconductivity, it has happened more than 40 years, right? It's nearly a career. So it takes time to understand things when they are explained with equations in textbooks. It can look a bit simpler, but it was quite a challenge to understand this. So what they came about for this theory to understand what was this superconductivity, they really they used the fact that these electrons, the charge, they are in a lattice of the superconductor, the material. It could be mercury, for example, and there are interactions between the free electrons and the lattice, and when some conditions are met, electrons are assembled by pairs, which are called now the Cooper pairs, from Leon Cooper, physicist. And Cooper pairs, they have a charge of 2e, 2 times the electron charge, and they are bosons. They are not fermions, so they don't have the same property as electrons at all. And they have all the good properties of bosons, like photons. Photons are bosons, of course. And so you can have with these Cooper pairs, even if they are in a solid state system, in a metallic, often metallic or solid material, you can have all the good properties of photons, like interference, diffractions, some effects that are not usually in electricity. So that was really one of the great achievements of this theory. So I'm going to try to explain a little bit in a simple way how it works, how we can understand the main properties of superconductors, just with hands and not by going to the calculations, which you can find in the BCS paper of 1957, and which is quite extensive with a lot of details and physics and equations. So let's see how it can be explained. So why you have electrons in Cooper pairs? That's the main question that we could ask. Usually we all know that with the Pauli principle, 2 electrons cannot be in the same quantum state, and there is repulsion between electrons. So how is it possible that they are together in a superconductor? A simple way to explain it is to represent these atoms. It's not really to scale, but I will don't want to go too much detail. So you have the atoms which are separated. It's not at all at scale in the lattice, and you have these electrons which are here, 3 electrons given by each atom. And when this electron travel with a certain speed, they are negative. The atoms are rather positive, right? These atoms close to the electrons are attracted very simply, naturally. And then they are a bit heavy, right, compared with the electron, much heavier. And finally, when the electron has passed and is already a bit further away, I try to explain it in a classical way, of course. There is no other way, even if the theory is purely quantum. So there are some approximations, you can understand that, but it allows to explain this, what we call electron-phonon interaction in the solids. So you have these electrons which are first electron which came here and which attracted these atoms, these ions, positive ions. When the electron has left, these ions are heavier. They didn't have yet time to go back to their initial position. And finally, it means there is an excess of positive charge in this area. And very naturally, it will lead to another electron coming here, which is attracted by this positive charge. So finally, you can understand that this electron with this one here, they are correlated in some ways through the lattice, basically. This is the electron-phonon interaction. So when you can consider that this global object made of the 2 electrons, this is what we will call, I have a problem with the tool anyway, this orange object, say, it's a Cooper pair, right? It's a Cooper pair, 2 electrons which are together, but not directly with an attraction. Of course, there is repulsion, but globally with the attraction of the ions, they stick together. So of course, this can only happen when you have a quite stable position of atoms. If you are at high temperatures, there are oscillations everywhere, and you don't have any order, and so this cannot happen. So you need to cool at certain temperature, at least with respect to some orders of energy in the material. So that's the way we can explain it, right? So this size of the Cooper pair, it's called the coherence length, right? Which is of the order. It can vary by a large amount, but typically of the order of tenths of nanometer. And that's one of the properties, and we will see other properties of this Cooper pairs later. So to continue on that, I will now pass to the first application, in some way an application of this superconductivity to make electronics. And the main device, though we can use superconductors in thin films, for example, to make detectors, to use a transition temperature of the superconductor to have sensors of like calorimeters, or to have also to sense the arrival of photons, which could make superconductor change become normal, and so the resistance will change. This is of course used for photon detectors. There are of course other ways to use these superconductors, and as long as you can make smart, I would say smart devices, like we have transistors in semiconductor electronics. And Brian Josephson in '62 made this prediction that you can have a supercurrent which can tunnel through a potential barrier, which when you place two superconductors very close to each other. And then he found that there are very interesting and not classical properties of this device, which we call now Josephson junction, and which is the basis for superconducting electronics, most of superconducting electronics, analog electronics, and also digital electronics. So he got this prediction during his PhD studies at the Cambridge University, and he was awarded the Nobel Prize in '73 for this discovery and prediction. I will come back, of course, on this after a bit later. And to finish the history of superconductivity, it's not finished, of course, and we're still waiting to have room temperature superconductivity in a simple way. But still, what was observed from Josephson and up to 1986 is that superconductors were not. We didn't find superconductors above 22, 23 Kelvin, which was really a limitation for applications, as you can guess. And so that was some people, I would say, left the field because they didn't see any applications at these temperatures. But by, let's say, surprise, I would say, as often happens in science, in 1986, Bednorz and Müller published an article that really has caused really a rebirth of superconductivity, and it's still active since then. Because they had discovered a new family of materials which called cuprates, which are made of copper oxides, and their material exhibited a superconductivity at an abnormally high temperature of 35 Kelvin. So it was not a lot, but still it was a change compared to what expected. And very soon after, a lot of teams tried to synthesize other materials, other kind of cuprates, and then there has been a jump in TC, as you can see on this graph. Right, we have the first discovery with mercury and then lead with Camerlin 1s. Niobium was discovered soon after in the 40s, and up to 86, temperature went really low. We were at about 22 Kelvin with this material, and then the discovery of Bednorz and Müller has led to this fast increase of TC based on cuprates. You can see you have copper oxides for all these materials. Other materials are still being discovered with low TC, and there are still new materials discovered more recently with this steel alloys. Okay, so that was really a change for a big change for superconductivity, and there is of course, and you will see during this conference and all conferences in the field, that there are a lot of activity in the material side of superconductivity. So how we can use now these superconductors, how they are being used, even if we cannot we need to cool down, there are still some fields for which it's very important to have superconductors, because there is no energy loss, the resistance is zero. And two applications, big applications, I would say, have been made from a long time ago in science and medicine. The first application that you probably know is MRI, right? Magnetic imaging, resonance imaging machines, which can create very high magnetic field, and they are made of superconductor wire. So you can fill this big coil, as you can see on the left picture, with helium or with other fluids now with higher TC materials. And when you fill this coil, okay, resistance will go down to 0. So you can produce high magnetic field without too much energy. Otherwise, it would be quite impossible to have a high magnetic field with a normal wire like copper. That's one of the applications which is very successful for medicine to make MRI coils. Another application is more related to science, and the Large Hadron Collider in CERN, close to Geneva, uses superconducting magnets, which are needed for this loop to let's say to concentrate the particles during the travel in this collider, and they required 7,000 kilometers of cables to generate magnetic field up to 10 Tesla. So it was really a big project, which is currently still working at CERN. And another application which is under development, which starts to work, is in Japan about magnetic levitation. This is a maglev train, right, which are suspended by magnetic levitation. They are based on superconductors, right? You can see here some superconductor magnets which are put on the train, and it allows to have the train going up to 585 km per hour. That's a record, and it is under construction between, I guess, Tokyo and Osaka for normal customers once it's finished. So that's one big application as well under development. So now I'm going to talk a little bit about the physics of superconductivity, because we need to understand it to go a bit more in details of with devices. So let's see now a bit of physics about bulk superconductivity, but really related to electronics, because we need to understand the electronic properties and electrical properties to use like Josephson devices. So bulk superconductivity, before talking about it, I'd like to mention a few books that I used, and I would recommend you to have a look on them if you want to understand a little bit more. Of course, what I'm doing is just a short course, a review. The literature about superconductivity is so heavy. Just for the Josephson junction, you can find books of more than 500 pages. So there is a lot of knowledge about this field, and I can recommend a few books that are quite nice. So I have one of this book is TeamCam, okay, TeamCam, which is called Introduction to Superconductivity. There is this is the old edition, but there is already there is a new edition, so which new, relatively new, which has already 15 years of age, but still it's a very good book to understand the bulk superconductivity and PCS theory and all the physics. It's mostly focused on physics. So that one of the books. Another one is which is really focused on electronics. This one is the one of Theodor van der Zeer and Turner, which is called Superconductive Devices and Circuit, which I would really warmly recommend. There are two other books which are very important. I don't have them here, but one is the one by Konstantin Likarev I will show you in the next slide the reference, which was published something like in the 80s, early 80s, There is also a book of Alan Cadin, which is really interesting for electronics. And when I will talk about squid, I didn't introduce yet the squids. You have really 2 volumes which are very important, which is called the Squid Handbook. First volume about theory and fundamentals, second volume about applications by John Clark and Alex Baginski, which I would warmly recommend. So a few books where you can find a lot of things. On my slide, I'll take a lot of examples and mostly pictures, figures from these books. So I would recommend you to have a look on this book if you want to go in the detail. So these books are there. This is the book of, I forgot to mention the book of Antonio Barone, Physics and Application of the Josephson Effect, which is really important as well for the Josephson junction properties. And another book that I used recently, which has been published just a few years ago, which is also takes back some content in some way, or the philosophy of the Baron in Paterno book, which is a book of Francisco Tafuri as editor of Fundamental and Frontier of the Josephson Effect. Okay, and you can see here other books, some of them I mentioned them to you. The references are there, okay, so you can also find a very nice forum which presents all the things about superconducting electronics. I can encourage you to see all the news about superconductivity, applied superconductivity, by following this link. And here you have all the references I talked about. There are other references which I will give at the end of the slides. But these are 6 important books, I would say, that we use. Every person working in this field in electronics at least must know. So now how to explain superconductivity and how to use it after with Josephson junctions. I will try to I already presented the fact that when because of the lattice and the interaction between the electrons, the free electrons in the lattice, you have Cooper pairs which are created basically from free electrons. When on the BCS theory, you can show that when you check the energy, the different energies available in the material, compared to with respect to the current density, you have a curve which looks like the one which is at the screen. It's maybe not so easy to understand, but basically what you can figure out is that when you have a metal, a normal metal, you know that the conduction band is not full. So basically, you have like a constant vertical. I can maybe show it on the screen. No questions. Seems that everything hopefully is clear. Okay, so the next video, we are going to start the next video. I'll go offline and I'll see you after the video, or maybe in the middle, we'll see. So to explain it in a simple way, when you have a normal metal, you have all these electrons which are filled up to the Fermi level, the energy of Fermi here, and the density of state, if you watch only closely to energy level, is both constant. When you reach TC, when you cool down a normal superconductor material, then there will be a condensation effect, basically a condensation in the energy referential, meaning that all these particles will go in the same state at energy level, and this is these Cooper pairs here, which are all at the same level. So this condensation, because yes, they are all at the same level, and they change the state, basically. They were fermions here, they were electrons, and they become bosons here, assembled by two. So meaning that all these, not all the electrons do that, only the free electrons, the ones which are not bound to the atom, right? Only the ones which are very close to this energy level. So since all these electrons by attraction through the lattice are assembled in Cooper pairs, finally some levels are forbidden around this energy level. So this is the second diagram, which represents another model finally, where you have if it's at zero absolute temperature, you have only one level accessible, and no level above with through a gap energy of which we call usually delta, and this delta times 2, because there are 2 electrons, is the energy that you need to break the Cooper pair to make two electrons in some way, 2 quasi-particles, because for some reasons I will not detail here. So at absolute zero, there is no electron here, they are all here. What you observe here is that the density of state goes to infinity, and this is what was also what you could see on this equation here, right? Where you have when the energy is equal to delta, you go to infinity. Here, basically, it means that the number of electrons is not infinite. Of course, just the density of state itself goes to infinity, just because since you have bosons here, they can all be the same state, right? So you can have a lot of states which goes to infinity. And after you go to a normal, you go back to the normal distribution, which is associated to the normal resistance of material. We'll see that a bit later. So basically, when you break a Cooper pair, you need 2 delta of energy, then you get 2 electrons, and they will be in this conduction band, but with this gap, which is really a property of superconductors. It's a gap which is much smaller than the gap of semiconductors. There is about a factor of 1,000. So it's a gap of the order of 1 terahertz, say, between 500 and 1 gigahertz and 1 terahertz. And that's a very important property of superconductors. There is another way to represent these energy levels, because we have a system with 2 kinds of particles, so it's a bit complicated to represent because the 2 physics of bosons and fermions are different, and it's always so there are graphical representation. This is one of them here, where you have only energy starting at delta from all let's say quasi-electrons and quasi-holes, we'll see why after, and otherwise you have these Cooper pairs at this level, Fermi level here. The other way to represent it is to use the same diagram as in semiconductor, where you unfold, I would say, this curve in 2 curves, where you have delta here and delta here, and you consider that you have, let's say, that's a valence band in somewhere, and this is a conduction band. This is the Fermi level where all the Cooper pairs are, and when you break a Cooper pair, if you assume we calibrate the energy, you change the referential. When you break a Cooper pair, you get you get one hole here and one electron, let's say here. So you have a difference of 2 delta of energy to have to go from this band to this one. It's another representation. It's a bit not so easy to get acquainted with, but it's a way to understand how the system will work, at least from a, let's say, photon assistant point of view, and also for in electricity and electromagnetism, basically. And also, we should say that the reason why we present it like that is we are, of course, not operating these systems at 0 Kelvin. We use them typically at Tc over 2 as a half the critical temperature, but it can be any temperature between 0 and Tc. And of course, at this temperature, intermediate temperature, you have two kinds of charge carriers in the superconductor. You have Cooper pairs, which are at this level, and some of them have been broken by thermal energy, and then they are in form of quasi-electron, of quasi-holes, and the way to represent it is to say that we have there are some electrons which have been excited here, and then since they are here, they took their energy from, they left a hole, right, if they move here. So we can consider these are holes and these are electrons. That's another way to understand it. So this gap is, as I told you, an important feature of superconductors of the order of 1 terahertz. And of course, you can understand, especially with the phase transition theory, that this gap corresponds to the order of the system. If you are at high temperature, the metal is normal, there is no gap, and there is no order. These electrons have collisions between themselves, and so you can consider the order parameter is 0 in phase transition. And then when you cool down the system, it becomes, I would say, superconductor progressively. The order increases at 0 K. You have a perfect order. All electrons are in Cooper pairs. They are phonons. They are bosons, and so they are in the same state. So there is perfect order. You have a macroscopic wave function associated to these Cooper pairs, and of course they have a perfect order, and the order parameter in phase transition is 1. And of course, in between, you are in a mixed state where you have both kind of particles, and then you can understand that the gap voltage or the gap energy, 2 delta, here is going from 0 at Tc to the maximum 2 delta at 0 K. This can be calculated, and the PCS theory provides accurate calculation of that, and we show that delta as a function of t follows this curve, which is typical of phase transition, with here you see a vertical tangent at Tc, which correspond to some discontinuities for some physical parameters. And there is, what you can see is that this gap doesn't change too much if you stay below Tc over 2. So usually when you want to have the good properties of superconductors, you always like to be below Tc over 2, and typically we use, most of the time we use niobium as a superconductor. Tc is 9.26 Kelvin, and when you are at 4.2 K, it's perfect, you are just below Tc over 2, and you still keep most of the good properties of superconductors while not having the difficulty to cool at very low temperature. But you can also use superconductors in this area where properties change very fast, and this is used, for example, for transition edge sensors, which exploit the change of resistance or conductance of superconductor when you are in this zone, because it's very sharp, so it's very sensitive as well. Depends what you want to do. So now that I presented the basic properties, and yes, I forgot to mention this one, BCS theory gives you as well a relation between this gap energy and Tc. It makes sense that there is a connection between both, because as I said, this delta, this gap energy is associated to the interaction, attractive interaction between through the lattice, And of course, if you are at you need to cool at lower temperature, lower TC to get superconductivity. It means the attractions between electrons is not so strong. Otherwise, superconductivity would happen at higher temperature. And then it means if it's not so strong, it means the gap energy is lower, which makes sense. So the gap energy is in fact linear with TC, at least for all low TC superconductors, and the relation is here. Okay, so now that I just gave a few hints about superconductivity in general, bulk superconductivity, we are going to go to the devices now, to electronics, to electricity. And the most important device, as I already mentioned, that has been proposed through after the work of Brian Josephson, is the Josephson junction. It's a very simple device, finally. It's just two superconductors which are separated by a very thin barrier. As I said, if it's a superconductor, it means we try to put it at a temperature where, let's say, Cooper pairs dominate the behavior. And these Cooper pairs, they are bosons, they are all in the same state. So they have you can model them with a macroscopic wave function. So that means, finally, that this cube here, this parallelepiped, can be very big, right? It can be 1 cubic meter if you want. If it's at TC over 2 or below TC, it's superconductor and it's a quantum object. So quantum doesn't mean small, right? Quantum can be macroscopic, can be quite big. When you see a magnet levitating on a superconductor levitating on a magnet, this superconductor is a pure quantum object, and you can see it. It's big, right? It's large. So that's very important to not to be confused. Quantum does not mean microscopic, right? Even if phenomena associated to quantum physics are of microscopic reasons, say the let's say quantum features can be macroscopic. So so here we have two quantum objects. Each of them can be represented by a wave function, which has amplitude, right, and a phase, just a phase. Like you are used to that in optics. For example, when you take an electric field, you have it's also a wave, right? Electric field, it's part of a wave, one part of the representation of a wave, and you are used to represent the electric field with an amplitude and a phase, right? And especially you need that when you do interference in optics or diffraction, for example. We have exactly the same phenomenon here, except that the quantity we use is not electric field, so it's not quantity related directly to the, let's say, difference of voltage associated to electric field, but here it's associated to the number of charges of Cooper pairs in the superconductor. So finally, the unit of psi here, it's in fact it's the square root of charge, right? So it's something which is solid finally. So we have the good properties of photons, but on a solid state system. So now if you take two of these superconductors and you make them not too far from each other, like a few angstrom or a few nanometers, maybe 1-2 nanometers maximum, this wave function is not just, you can calculate that with quantum physics, it's not just sharply going to zero here, because you have uncertainty principle as well. You have a relation between energy or between position and momentum, etc. So you have a wave function which has an evanescent, which is evanescent on the side, like for any system, in fact. And if this barrier is thin enough, these two wave functions, if you take them separately, you see here, they overlap. Basically, there is an overlap in the barrier, meaning the properties in this barrier here, meaning that the wave function, the total wave function is not zero first, and there is a phase which is going to vary over this distance, and that gives all the good properties of Josephson junction. right? Depending on this distance, depending on the properties of the barrier, you can have different wave functions here, and you can see very interesting features. So I'm not going to do here all the demonstration about that. The best way is to check the paper of Brian Josephson of 1962 or 63. The demonstration is not very complicated. In fact, it's maybe 2 pages, and you can really find very nice properties of this device. And what is interesting in a device like that is to calculate the current and see how it depends on these wave functions. So the parameter which is the most important in the Josephson junction is phase phi, which is phi2 minus phi1. It means the difference of phase of the two wave functions of these two superconductors. That's really the important parameter. So after Josephson made his theory, there has been some people trying to understand how it works, how the currents evolve in this device. As I said, there are 2 types of carriers: Cooper pairs, which are bosons; quasi-particles, which are fermions. So this work has been developed in particular, but not only, by Wertheimer in 1966, Harris, Larkin and Ovsevnikov, and many others, who tried to understand all this. And what comes out of the modeling of these devices is that the current which crosses the Josephson junctions has 3 terms, basically. One which is called often IJ1 times sinus phi. This phi, which is the phase, the difference of phase between the 2 superconductors, which is the Cooper pair current. Okay. We'll come back to that a bit after. And there is also what we call a cos phi term that we usually neglect. In most of application, we neglect it because it's not very important below the gap energy, the gap frequency. It means unless you are close to 700 gigahertz or 1 terahertz, it's negligible. So far, up to now, we mostly forget it, but it becomes now more important as technology evolves. Now we are able to indeed reach these frequencies, and we need to take this term into account. So these 2 terms are about Cooper pairs. You see that they are out of phase, these 2, 90 degrees phase difference. It means you have, when you go at high frequency, you make the system oscillate in some way. It is at the gap energy, it's a characteristic energy, characteristic frequency, and the system has a response which is not in phase with solicitation, if you want. So you have 2 kinds of currents, one current in phase and one out of phase. The same way, like if you have an oscillator or a pendulum, if you try to excite it at its resonance frequency, it starts to change, right? It cannot follow your pace, and then it's going to be dephased, and these terms becomes important. So that's the first 2 terms, and this third term is a quasi-particle current, the one which is associated to the Cooper pairs, which are broken by just thermal environment, and they are electrons, or quasi-particles, as we should say, that also flows through the junction by tunneling, simple tunneling. There is another way to write. We can calculate the current. Here it's as a function of voltage and temperature, but you can also calculate the dynamics. It's more complicated in this case. The dynamics, the full dynamics of a Josephson junction. And you can show that this current that you will observe is the imaginary part of this complex integral, where you have 2 terms, S and R, which are green functions associated to the Cooper pairs and quasi-particle. So the formalism is not very simple, I must say. It is quite sometimes a headache to go in the theory to understand it, but it's all well understood now, and you can use results in the books that are in the books now and well detailed. But of course, it's important to have a knowledge of that if you want to do and I hope you will have to do that in the future. We are in a state now where we need to do Josephson junction barrier engineering. We need to engineer the barrier, not just use simple barriers that have been done historically. And to do engineering of barriers, then you will need to play with this equation and try to optimize the barrier to get the good properties that you would like to have an ideal device. For the moment, the device we have is the best we know to fabricate, but we don't, they are not constructed atom by atom, I would say. So if you check these currents of Cooper pairs and quasi-particles, you can see as a function of the gap energy or gap voltage, if you want, about the voltage across the devices, which is normalized to the gap energy at 0K. You can simulate and you can model and of course simulate as well the currents of Cooper pairs. These are these two curves, and quasi-particles, these two curves. So this is what we call the sinus phi term here, which is the term that we usually use at any temperature, at least at Tc/2, because this is the dominant term of Cooper pairs, and you can see in particular an important property is that at 0 voltage the current is not zero, right? Which is one property of Cooper pairs and of superconductivity. You can have a current without voltage, so you can have a displacement and without spending energy because the voltage is zero. And you have this evolution with, of course, a feature at the gap energy. And you can also see this cos phi term, which is important when you reach high frequencies, or when you also have a Tc close to when T is close to Tc, because in this case you are close to the gap, right? The gap is small. And then this term is more important, but if you work at Tc/2, you will have a curve close to this blue one, and you see this term is nearly zero all the time, except, and it starts to be important after you pass the gap energy. So this is for Cooper pairs. And for quasi-particles, you have this curve. The imaginary part corresponds to the current in phase with solicitation, with voltage, I would say. And at 0K, you have this curve, as you can see here, which is very, very nonlinear. I'll come back on that later. And when you increase a little bit the temperature, you can see how this IV curve is transformed. And at Tc it becomes normal resistance, because it's just a normal metallic wire, I would say, resistive wire. So this is imaginary part of the quasi-particle complex function of quasi-particle current, which is what we measure usually. But there is also a real part which is connected to this one. In fact, you can go to find this one through Kramers-Kronig transform of this curve. This is due to a causality principle. And again, it's connected to the fact when you have a system like a resonator, the phase is not independent from the amplitude, right? In a resonance, you have two curves. You have amplitude curve, which is like a shape, like a bell shape, and you have also the phase which goes through zero, and not necessarily through zero, but which is odd function, right? And this curve corresponds to this out of phase current, which also are not usually very important at low temperature, at low voltage, but which become important at the gap energy. So you could say that it's not true. You see, at zero there are currents which are important, minus 75 normalized to the critical current. But if you check the current of the Josephson current here, Cooper pair, I mean, it's the exact opposite. So basically these two currents cancel each other, and what you measure is zero, usually zero for out of phase currents. In any case, when you measure a device, a real device, you cannot separate Cooper pairs, of course, and quasi-particles. You measure a current, and that's it, right? So this is a model, and you need to do the sum of these quantities, the way it's done here, right, with this sinus phi, cos phi, to have the real current on the device. So here is for these two currents that can be that are important to know. So as I said, the important parameter for the Judson-Cooper pair currents is the phase difference between the two superconductors. Of course, depending on the barrier, depending on the way the materials are manufactured, depending on the temperature and many other parameters, this phase can have different variations, relation with the current. The current is a consequence of the difference of phase, basically. So the most important formula that we always use is this one, is this current, Judson current. I'm just talking about the Cooper pair current, is a critical current, a maximum value that you can have, times the sinus of the phase, basically. Right? This is the most important current. And so you have other models which describe this formula in more detail, but let's say that the simplest model is this one, and you can also have other ones with transparency of the barrier taken into account, and there are all kinds of other models you can see with different equations, depending if you are in the clean limit for the superconductor, if you are in the quantum regime, if you have several channels, let's say tunneling channels, you can have short circuits or kind of how it's called, point contacts in the through the barrier. You can also use not an insulator but a normal metal, and depending on all these parameters, depending mostly on the barrier properties, you have different relations. But most of time, for the junctions that we know to do, which are not extreme in their properties, I would say, classical devices, this formula is enough to understand most of the behavior. If you see how this current varies with the phase, you see that depending on the different cases that I mentioned here, you have different curves, right? So the most well-known is this A curve, blue, which is a sinus, right? Basically, it's a sinus. I is sinus of phi. But you can see that in some cases you have a very strange behavior. You can have multi-valued systems, and also it depends on the temperature and the proximity effect in case you have a thin layer of normal metal in the barrier, etc. And all the difficulties to find, to correlate, I would say, your real device with the good model which fits with it. Hello, everyone. I'm back. So I think there were two questions for the last video presentation. One by I think Luigi Di Palma about the phase current relations of slide 22. So this slide 22 was about there was a table with a lot of currents for different models of Kulik, Melianchuk, and other. So is this the question was about the calculation where they derive from the calculation by Harris. So what I should say is this calculation by Harris is derived from the one by Wertheimer. which calculates tunneling currents as in the barrier. And of course, when they did that, they assumed at the very beginning a simple barrier with homogeneous properties. And what is done is basically a calculation of probability of presence of charges on each side of the barrier. Right, and depending on that, you can, if you make a coefficient of transmission, you give a parameter, you can get the expression of Harris and or Wertheimer. With all these other models that you saw, where there is a transparency, etc., this, of course, is based on the work by Wertheimer and Harris, but the models have been improve to take into account the real properties of the superconductors and the barriers. And especially the barrier is not perfect. There is also a roughness, a rugosity between the superconductor and the barrier. There can be, if there is, if the superconductor is not perfect and has a little metallic thin layer, like aluminum, when you do with niobium, you have aluminum oxide barrier and there is a bit of aluminum, then the barrier properties are different. When all these models take that into account, they assume different kind of barriers, different kind of superconductors of order as well, different kind of epitaxy, and then the consequence of that, it will change transmission parameters. They are not necessarily homogeneous over the barrier. You can have also some what we call pinholes, sometimes some channels, like when you have a lightning, you have some channels which are operating in parallel with quantum tunneling, and depending on all these parameters, you have different models and different results as well on the phase versus current relation. And after, to know which model is good, you need to compare with experiment basically and try to fit the right model for that. So yes, that's for this answer. The other question was, in fact, I should have answered before by Manel Mas-Martin. The phase difference, what I talked about, is indeed the phase difference between the two wave functions from the two electrodes of the superconducting Josephson junctions. Each phase, each wave function has its phase, phi 1 and phi 2 respectively, and the phase, what is important is the difference of phase. You should understand that in Josephson junctions, the phase difference, it's like an energy difference in what we are used in the classical world. Because you have a phase difference, meaning you have a difference of probability of presence of current of charge density on each side. If you have a difference of charge density, you will have a current flowing from the more densest part to the less dense part, like you have with molecules. If you take two reservoirs with molecules, one with high pressure, one with a low pressure, when you open them, the chemical potential, it means the Fermi level is not the same, and then you will have a flow, a natural flow of current of molecules between these two reservoirs. It's a bit the same. It's a bit the same, but it's the phase is a parameter which allows for this movement, and that's why we cannot understand everything just with the usual property of intensity, like in optics. You have, I mean, the important parameters in optics is the electric field. The intensity is the square, but when you calculate the square of the electric field, the phase disappears. Then you have parameter that you phenomena that you cannot understand if you don't take the phase into account, like interference and diffraction. It's exactly the same with Josephson junctions. You can make a full analogy. That's it for these two answers. I don't know if there are other questions. And if there are no other questions, we will go to the third recorded video, which is a bit shorter, I guess, about 20, maybe 20 minutes. And then after, I'll take again questions. And then we'll go to the fourth part of the course, which will be fully live with a PowerPoint. It's a bit more risky, but we'll try it. Thank you. So to understand the tunneling effects in a Josephson junction, it's sometimes useful to represent the junction like it is done on this slide, where you see the vertical barrier in the middle, and with diagram of energy bands of each superconductor, S1 on the left with energy level mu1 and gap energy delta 1, half gap, and the same on the right for the second superconductor S2. And you can understand on this small sketch that of course you have two kinds of current which can happen with Cooper pairs, and Cooper pairs can cross from mu1 to mu2 where they are aligned, right, when there is no voltage. That's why there is a current at 0 voltage for a Josephson junction. But if you apply a voltage between the two superconductors, you see that Josephson Cooper pairs are not at the same level. They cannot really cross. At least there is no DC current if voltage is not 0. But you can have quasi-particle currents, either because the voltage is high enough, so you have let's say electrons from or quasi-holes from the one superconductor, which can cross to the other conduction band, free conduction band on the other side. And you can also have currents due to thermal effects, just because the temperature excites a few electrons, or if you want, it breaks a few Cooper pairs, and they can be present even if you don't apply a voltage. So you can imagine, depending on the voltage, different configuration, which where you will have a higher current. So you have one current when mu1 is when the voltage is mu1 minus mu2, or the opposite, and also when you have a voltage of the order of the gap. So how does it look like now on a curve, at least schematically? You can see here that if I just consider the quasi-particle current, right, just one associated to this hatched part, but you have no, if delta 1 is delta 2, it's the same superconductor on each side, you have just current which can happen at 0 voltage, a little current sometimes, and the main current is at the gap and above. Why at the gap? Just because you have at the gap voltage this level is just across from this one, and you have infinite density of state here and here, so you have a photon assisted tunneling in some way, or at least voltage assisted tunneling from this part to this part, and it's very steep, right? It goes from 0 to this very high current density of state, and then when you continue to increase voltage, you get to this, let's say, linear part associated to the fact that the density of state doesn't change, and that it corresponds to this here, this slope that we call the normal resistance of the junction. So here you have the gap, here it's a normal resistance, and you can see a peculiar feature. If mu1 is different from mu2, the superconductors are not the same on each side of the barrier, then when the voltage is equal to the difference, you have also a small current which can happen, and you see clearly that well, you see it from here, but you can also see it from here, where you have these electrons here that we can cross on this part, and it corresponds to this small slope. So this is the theory. Basically, this is the theory. When you do measurements and you, for certain kind of junctions with some resistive barriers, you see that the IV curve doesn't look exactly like that. It's because mostly this part is due to the Josephson current, not the quasi-particle current. Still, we see the normal resistance part here, and you have a transition between both, which is due to the fact that it's not just a pure Josephson junction, there are some resistance in parallel. If you fabricate a junction without resistance in parallel, okay, you have another IV curve. Well, you see this IV curve here is correspond to this junction with some, or at least not exactly this one, but okay, we have measurements associated to a junction with which is here. I'll talk later about technology of this junction. And you have a resistor here which is in parallel with the junction. So basically it corresponds to this this kind of curve. But if you have no resistance, you see that you have the Josephson current here, always when there is no voltage. And when you reach this maximum value, what we call the critical current, then you jump here, meaning that the current goes through quasi-particles and not Cooper pairs, mostly quasi-particles. And quasi-particles are electrons, okay, so are associated to a non-zero voltage, and basically the gap voltage here. It corresponds to, if you want, to this curve where you have this energy aligned with this one, or the opposite, this one with this one. And then you have this fast tip, and then you go to the normal part here, which corresponds basically when this linear part is across from this linear part, or this constant density of state. So when you increase the voltage, you see that you have a number of electrons which can cross from here to here, which increases linearly with the difference of voltage. So that is some feature that you can see on the current voltage characteristic of Josephson junction, depending on how it's fabricated, on the properties of the barrier, and many other parameters. But that's the simplest case. It's just when you bias it with a DC voltage. If you want to solve the equation that I showed before, and you apply on top of that not a DC voltage, but you need to apply a DC voltage, but you can also apply a microwave voltage signal, which is typically of the order of a few hundred gigahertz. Here you have 2.8 millivolts. This is an niobium junction, so typically it's 700 gigahertz here, as in terms of energy. So if you apply a signal, for example, of 400 gigahertz, which is about, in terms of voltage or energy, this distance, you can simulate the IV curve, and you see that this change, and you can see here some slopes, and this length of slope is h nu. Basically, the voltage times E times the electron charge is h Planck constant times the frequency. Here it was a signal of 380 gigahertz applied, and that is when you suppress, in fact, when there is no Josephson current, just with a quasi-particle current. If you have both quasi-particle currents and you don't suppress Josephson currents, or there are Josephson current and quasi-particle currents, and you apply a signal at 380 gigahertz, you can see how the IV curve, it's a measured one, can be very complicated. Because the current, the voltage, the gap is about here. Without Josephson current, you see this curve here, which is a measured one, right? It goes here, which looks like this one. It corresponds to simulations, basically. But if you have on top, if you have Josephson current, and also, of course, this microwave signal, you see how the curve is quite complicated with no current here, some small steps here, some very sharp steps, etc. So it can be quite complicated. The electrodynamics of a Josephson junction is complicated, and that is one of the main difficulty of these devices. These calculations are not simple, so you need software to do that. Otherwise, it's very difficult to predict. things, or at least you can predict things only in simple cases. So why we would apply electromagnetic signals at these frequencies is because these frequencies are the order of the characteristic frequency. It means the cap frequency of Josephson junctions. And then at these frequencies you can have very nice properties due to the nonlinearity of the device, and you can see how nonlinear it is. It means if you apply different signals, you can have multiple harmonics, for example, and if you have applied two different frequencies, you can get the difference and the sum of this frequency. So you can do frequency mixing, and it's very interesting for receivers, for microwave receivers, to convert a signal from a high frequency to a lower frequency. It's usually used, for example, and historically for radio astronomy, where you can use these devices to take signals, to measure signals in a sub-millimeter band or terahertz band, and convert it to lower frequencies by mixing, I would say, the signal that you want to detect with a signal applied on board, which is we call a local oscillator signal. And when you have and you can get the beating between these two frequencies and get the spectrum that arrives that you want to measure, but at a lower frequency that you can put, say, on an oscilloscope or fast spectrometer. So this is just a few examples of the complexity and the very nice, beautiful properties of Josephson junctions. For this overview, I would say, and the other lecture will talk a bit more about specific properties of Josephson junction. I didn't talk yet about magnetic properties of Josephson junction, which are very important. But okay, it gives you a first hint about these devices, I hope. So we're back live. Are there any questions on this recorded presentation? No questions? Okay, so in this case, we can continue with the fourth presentation. This one will be live with a PowerPoint presentation. It's quite long, I would say. So we'll make a break in the middle. I'll see where, maybe after 30-40 minutes. Okay. So I guess you should be able to see the first slide, right, which is very general. So we are going to start with it's a fourth presentation, but it's part 2 about Josephson junctions and squids. So far, I presented mostly the physics and the basic physics and basic, I would say, electronics of these devices. Now we are going to go to the details of these Josephson junctions. So just to give an example of the Josephson junction, it's also in some way equivalent to the transistor for semiconductor electronic. Just it's a bit simpler in its fabrication. There are only two ports, not 3, and but the physics is more complicated, I would say. So it's usually different techniques to fabricate these junctions. Historically, that was a very simple way to do it. You take a piece of a superconductor, it could be niobium, could be lead, for example, and you let it in at room temperature to have a bit of oxidation. This oxidation is usually a very thin layer of a few angstrom or nanometer. And after you take a wire of another superconductor material, you make it sharp, right, to have like an arrow, and then you press against the other material, which is insulated. And if you press enough, at some point you will have the right, I would say, thickness of barrier made by the insulator, which is which covers the first superconductor, and you have a Josephson junction. And since it's sharp, the area is quite small. It can be a few tenths of microns, and then you can observe. Then you need, of course, to cool this, and you need to do this mechanical pressure of the wire on the other superconductor at low temperature with a mechanical system. We call that point contact Josephson junctions. That was really the original fabrication of this way to fabricate this. Of course, with this, you cannot go very far, right? You can make them, it depends on who does the work. So little by little, lithography technique have been used, and here you have on this slide an example of Josephson junction made at IPHT in Jena, Germany. So you can see down here, you have I will not explain all the details because it's not just a Josephson junction. The Josephson junction is just this round part here, which is here. The barrier, you cannot see it. The scale is 3 micrometer. The barrier is about 1 nanometer. So you have here the base electrode, is niobium. Then you have this thin barrier. You have also insulators here that you don't see. And you have the upper electrode here. And this is the Josephson junction, basically. In this case, it's a bit more complicated. You can see if you follow the superconductor that you reach this small layer here, which is a resistive layer. It means it's a resistor, simply a resistor, this rectangle. Then you continue here. Here you have a via, a short, basically, between these two electrodes. So the current can go here and comes back. So you have a resistor in parallel in this case. It's done for digital application. I'll explain a bit later. But usually you don't need this part, right? You just have this junction. And of course, you can understand that with this technology, since it's done by lithography, you can fabricate hundreds, thousands, and even now nearly millions of junctions on one chip with this technique. So that's an example how it's done. I mentioned here the symbol for this Josephson junction. It's not the official symbol, but now there are two dots here. But basically, when you see a cross, it's a Josephson junction. That's the symbol that we use for this. So next slide is application of the Josephson junction. I'll just show you here an overview of some applications. I already talked a little bit about magnetic field imaging. It can be used, well, we saw this RM picture, resonance imaging, MRI imaging, sorry. And but there are also other techniques for medicine which are used with magnetoencephalography or magnetocardiography, where we use squids. I will talk about squids just after. But you can cool and put on helmets or on this system, and you have basically it's a liquid helium dewar. You have the device here, and you can sense the body of the person. You can measure the magnetic field. You can also use this Josephson junction to measure the magnetic field in geophysics, because there are some. It's a bit like this metal detector, right? But more sensitive. You can find traces of ferromagnetic materials, or even which are sometimes connected to gold or diamonds. Rocks underground, so you can do that with Josephson junction devices embarked in a plane. Here it's a squid. The Josephson junction are on this dewar here at the back of the plane. You can also use it for spectroscopy, because as I said, its characteristic frequency is typically of 700 gigahertz. Meaning that you have you are sensitive in this range of frequencies, and this is where semiconductors are not very sensitive. Usually, semiconductors are very good at high infrared wavelengths because of their gap is in the infrared range. Superconductors are better in this terahertz range, which is between let's say high frequency electronic and optics and infrared. So spectroscopy for science, for security. You can see through for example, through clothes, so you can see if there are some weapons. It is also used in spectroscopy for radio astronomy to analyze signals emitted by usually it's a cold universe, I would say, all the dust, interstellar dust, mostly all the molecules which are at low temperatures. They have emission lines in this range of frequencies, typically from 10, 20 gigahertz up to a few terahertz. So these are the detectors which are the most used. And I would say astronomy was the main driver of the development of Josephson electronics for many years. Now there are new applications, but for many years radio astronomy was the main driver, and most of radio telescopes in the world use detectors with Josephson junctions, in fact. And it's also used in metrology, because we have a very nice property that I will talk a little bit after of Josephson junctions. There is a frequency versus voltage relation, which is quantum. You have the Planck constant and divided by twice the charge electron as a constant between voltage and frequency. And this is, since we know to measure times and frequencies very accurately, we can calibrate voltages very accurately. So all the instruments in the world are calibrated with what we call Josephson standards. It's a simple array in series of a lot of Josephson junctions, like here, and you can have several thousands. And when you apply a frequency, which is well controlled, you can obtain between the two electrodes the voltage, which you arrange yourself to have a round value like 10 volt or 1 volt. Then you can calibrate all your instruments. So that's very important for metrology. And the last application that I'll detail in the end of the talk is digital electronics. You can also use this Josephson junction to make digital electronics. This is a bit behind all this analog application, but much more complicated and powerful in the end, because you can make signal processing and microprocessors, and there is a lot of development currently in this field to use Josephson junction. And there is another field that I didn't show in this slide. It is you can still use the Josephson junction in a different mode when you cool them very low temperature, typically 10, 50 millikelvin. Then you can have a quantum behavior, a full quantum behavior from a point of view of a wave function control, I would say. So you can make artificial atoms with Josephson junction when they are very cooled at very low temperature. Then you can do some quantum computing. So this is Josephson junction has been used for the first artificial atoms for quantum computing. And now, of course, there is a lot of, as you know, quantum is developed all around the world with different techniques, with some optical techniques with real atoms, or with some semiconductors, qubits as well, and superconductor qubits are based on Josephson junction are also a solution. They have the disadvantage of needing to be cooled at very low temperature, but they have other advantages in terms of sensitivity, and also it's quite easy to make complex circuits with them. So that's an overview of the application, and we are going to see a few of them now. So I will start with, I take back the description of this Josephson junction in a very simple way to explain how they are usually made. So you see you have this barrier of 1 nanometer. Typically we work in with microelectronics techniques with thin films. Thin films meaning typically 100, 200 nanometers of thickness. The most used superconductor is niobium because it's very robust. It keeps its properties over time, over decades even. So it's the most developed, and for this reason, it has a bit, how to say, made some shade on other materials. Aluminium is another very good one. The problem with aluminium is TC is very low, and then you need to cool below 1 Kelvin to use these junctions, and so it's a bit more complicated from a point of view of cooling. Niobium is good because TC is 9.26 Kelvin, so you can work with liquid helium that you can order easily, and you can plunge your device inside a liquid helium tank, for example. Then you are at 4.2 K and you have the good properties. If you see this junction, I talked mostly before about this part. It is a quantum current. A tunneling current. This tunneling current can be either Cooper pairs or quasi-particles. But as you see the device itself, obviously, for pure geometrical reasons, there is a capacitor. It's a very thin barrier, so there is a high capacitor, and it has some influence. And basically, if you don't pay attention about this capacitor will shunt completely your device because it's a high capacitor with a high capacitance, and then it will shunt the high frequency signal. So even if the device can go at 700 gigahertz, the capacitor will shunt it unless you pay attention about it and you try to resonate it, at least in some frequency range. I put back the explanation of the wave function, right? Wave function on each side has an amplitude and a phase. And phi, again, it's a difference of phase between these two superconductors. It's a symmetric device, right? So all curves are anti-symmetric. And so you can use phi1 minus phi2 or phi2 minus phi1. It doesn't make big difference, right? There is no polarity on this device. So there are two equations. I saw before that the equation can be much more complicated, but I told you that most of the time we use the simplest case if we assume the junction is quite, let's say, made in a normal way, without any particular property. You will have this current dominating the Cooper pair current. The cos phi term we can neglect. For the moment, I will not mention it. I will not mention as well for the moment on this equation the quasi-particle current, because of course the Josephson current corresponds to a zero resistance, right? You can have a current without voltage in DC, at least at DC in continuous with continuous signals, and then it means it's a shunt in some way. So the current will not go through a resistive path if it can cross without resistance. So that's one thing. The second thing, which is I didn't make the demonstration done by Josephson about the phase variation of phase over time, but you can find that in most of good books. In the end of the calculation, you will find a second equation, which we call the second Josephson equation, which tells you that the derivative of the phase over time is connected to the voltage. So it's a bit strange because I'm talking about voltage, and I told you there is no voltage. But in fact, here we are talking about time variations. And as soon as you have a time variation, right, and you have a current, without even talking about Josephson junction, if you have a current, you have a magnetic field. If the current varies with time, the magnetic field varies with time, so the flux varies with time. And we all know well these Faraday's laws, right, which tells you that if you have a variation of flux, you have a voltage which appears across the device where the current varies. So this is Faraday's equation, in fact, if you check carefully, because there is a constant here. I will talk about it after, but basically this, you see that if you put this constant on this side, this variation is a variation of flux, right? Phi naught is the quantum of magnetic flux. It's h over 2e, Planck constant divided by 2 times the electron charge. It's about 2 × 10⁻⁵ Weber. And what this second Josephson equation says is that the voltage across a junction, if there is variation of current, if you impose a variation, is a derivative of the flux. This is just Faraday's law. This is Faraday's law. And what is interesting about that, in fact, is Faraday's laws was Faraday's proposed, understood this phenomena and before quantum physics was invented, right? So he didn't know anything about quantum physics, and he proposed a law. As you know, it's something you accept as it is. It's connected, of course, with Maxwell equations. And clearly, from this equation, we see that this second Josephson equation, this Faraday's laws has some quantum origin, even if it's a law, and basically it means that, and that's something very interesting that for I would say quantum electronics and superconductor electronics, is that finally the phase, this phase of Josephson junction here, this difference of phase, it's something a bit theoretical, right? You learn that in quantum physics. You have a wave function, and you learn that the probability of having an event is the square of the wave function, etc. It's a bit, it's a very formal theory. It looks mathematical, not very. The physics is not so obvious. It's quantum. It's not too intuitive. But finally, with this equation, you see that this phase, which is a quantum parameter, say, is just a flux, magnetic flux. So magnetic flux is something easy to measure, right? You can take a magnetometer, you measure the field, magnetic field, and over an area you will get the flux. So finally, with a quantum device, we can measure, we have access to the phase of the wave function just with a magnetometer. So this phase of wave function is something which is not so magic, right? It's something very physical. It's connected to the magnetic field in some way. So that's the two equations which govern Cooper pair currents and I would say the electrodynamics of Josephson junctions for the Cooper pairs. Not for I'm not talking about quasi-particles here. And these two equations, they have an advantage. They are very simple, as you can see, and you can calculate a lot of things. The first thing you can calculate is that you can observe that if you take a constant voltage, 0 or another voltage, whatever, the variation of phase over time is 0. Simply, it means the phase is constant. It means here the current is constant. This is what we call the DC Josephson effect, right? If you have a 0 voltage, you have a constant current with a phase, and this phi naught here, it is basically, mathematically, it's a constant of integration, but physically, it's random value. So it can take any value when you cool. It depends the way you cool the superconductor. When it reaches TC, there is organization of electrons, I would say, and the lattice. And when you cool down, when you pass TC, everything changes behavior because of this phonon-electron interaction which appears, and you have a resulting phase, phi naught, which will fix this maximum current. You understand that the maximum current is IC. We call it a critical current, and it will fix the maximum current in the Josephson junction. So depending on how you cool, you will see this current, not always the same on an oscilloscope or with a voltmeter. And it means it's very important to control the way you cool a device, depending on what you want to have. And I would recommend when you do experiment, if you want to have the best properties, you want to maximize usually IC. So you need to maximize IJ naught. So you want to have the sinus to the value of 1. The best way to do that is first to pass no current at all when you cool down. The device should have no current through its terminals. And the second is to cool down in a very controlled way, very slowly. to make sure you get the best configuration. It doesn't, and also third point, you need to have no magnetic field. As we will see, magnetic field is very important external parameter for Josephson junctions. So you need to cool in the best condition, in the quietest condition as possible to reach this IC. Depending on, so if you do 10 times the experiment, you will not always get the same value here. It depends on the phase. So that's the first property, DC Josephson, which we call it the DC Josephson effect. You can see a current without voltage. This is the absence of resistance, right? Main property of superconductors. And another thing that is interesting here is that if you put a constant voltage, right? You see that the derivative of the phase is constant, meaning that the phase increases linearly with time. Phi is 80 plus phi naught, right? And if you put this phase here, you see that you have a current which is a sinus of constant times the time plus t, so you can call it sinus omega t plus phi naught, right? And I removed the constant of integration, but there could be one. And you see this constant of integration is 2 pi over phi naught times V naught, the constant voltage you apply. And obviously, this is a sinusoidal current. And if you calculate this constant here, okay, it's a 2 pi, what we call Fj, it means Josephson frequency, but you can also call it omega j, Josephson angular frequency. You have, because of the value of phi naught, of the quantum magnetic flux, you have a frequency which is 484 gigahertz per millivolt. So if you apply 1 millivolt constant across this junction, you will have a current oscillating at 484 gigahertz. And this is where I told you before about the voltage standard and metrology application. This is where this relation is very important because it's simple, right? So if you apply, usually we work the other way. We try to apply a frequency and then we will deduce a voltage. Basically, because both are connected by this relation that the frequency is Josephson frequency, the voltage divided by phi naught. So it's very simple, right? And this is a fundamental constant, meaning if you are accurate with your frequency and time, and we know to be accurate to the at least 10 to the minus 15 today with some atomic clocks, for example, then you can have a voltage very accurate, typically 10 to the minus 11 relative voltage. So you can be very accurate, less than a nanovolt for a signal of several volts, so it's very accurate. So it is used in metrology, and I will not detail too much about the properties of this because it's a field by itself, right? So many people work on metrology in all metrology institute in the world, NIST at the USA, PTB in Germany, and in RIM in Italy, for example, but there are a few where some groups are maintaining these voltage standards. So this is a DC voltage standard. You can find the DC voltage accurately. You can measure it and you can calibrate it accurately. There are also AC standards which are developed on Josephson junction. It's current developments, I would say, and I will not talk about it because I cannot talk about everything. There are a lot of things, but today the work is based on using the same Josephson junction in different modes to do also AC standard, meaning you are able to fabricate in a quantum way a sinusoidal AC signal of a few kilohertz or megahertz, and then you can use as reference. So for these junctions, I already talked about this what we call Josephson branch here, right? When you have only the Josephson current, you have zero voltage and you have a current. You can go to the maximum of IC, not more. If you try to go above to impose more current, since the device cannot doesn't have in some way enough Cooper pairs to handle this, the rest of the current will be with quasi-particles. You don't have choice. And these quasi-particles, they follow the Wertheimer and Harris, let's say, models. They have different properties, and we can show, and I showed you before, that you have this kind of shape here, which is connected to the density of state of quasi-particles in two superconductors. And you can understand it here easily. If you have zero voltage, you have Cooper pairs on this Fermi level, right? And then I will answer the question just after this explanation. You have this Cooper pairs current here, which correspond to this red branch here. And if you apply a voltage, you see that the Cooper pairs cannot happen, at least DC Cooper pair current don't exist because they are not aligned. But you can have current from this superconductor to this one. And these are quasi-particle currents, and this one are associated with the resistance. And this is the sharp increase that you see here when you reach a gap, when the voltage reaches a gap, when this point is at the voltage of the gap with respect to this superconductor. And here you have this very sharp rise because it's connected to the infinite, quasi-infinite density of state. But when you continue to increase the voltage, you see that you go to this constant density of state, and when you increase, you will just have a number of electrons which can pass proportional to the voltage. So you have this linear part, which we call the normal part, because it corresponds finally to the normal density of state of the metal when it's not superconductor. And we call that a normal resistance. It's a very important parameter for Josephson junction. So there is a question by Andrei Pankratov asking if concerning the slow cooling of critical current, if when we are talking, for example, of 100 millikelvin, what does modern dry dilution cryostat provide slow enough cooling, reaching the base temperature in 24 hours? Frankly, I don't know to answer that. I never used this dry dilution cryostat. What is it's quite how to say, the condition you need to have it really well controlled really depend on a lot of parameters, not only the Josephson junction itself, how it's fabricated, is the barrier homogeneous or not, how is the epitaxy of the let's say the connections between the different planes, between the different superconductor and the barrier, and also depending on the about electromagnetic environment. Is it clean enough? We can shield the magnetic field more or less, and it will have an influence on this cooling. But of course, it will have an influence. I would say that usually when I'm talking of cooling down slowly, it means just a few minutes. I mean, around the TC, you do it in a few minutes, and not like in a few seconds, like plunging a device in liquid helium. So with this very low temperature system, usually they cool very slowly because I mean, it's difficult to extract calories at low temperature. But you need to be careful when you arrive to TC, basically around TC, and usually you go down a bit faster around TC because you are still at higher temperature. So I think with this kind of system, usually it's not so bad. You get often the good condition, but you need to shield very well magnetically, and also of course electromagnetically. But usually it's stone because it's a Faraday cage. I don't know if it answers the question, but at least I tried. Okay, so you have this Josephson junction where you have a mix here with two kinds of carriers, Josephson, Cooper pairs, and quasi-particles. So when you increase the current, you switch here, when you go to this linear part corresponding to this part of the current density, when you go back, you need to make an energy calculation, which I didn't make here. But you see, it's better, it's more energy efficient to go this way. So you don't go back here. You go down on the gap voltage. It means you have mostly quasi-particles controlling the behavior. And only in the end, you go back here and you can recover, in some ways, the Cooper pairs current. So the slide arrives. Squid. I didn't talk yet about squid. Well, I said the word, but I didn't explain. Superconducting quantum interference devices. So it's a very, it's a very fundamental property of this quantum electronics, or phase electronics, is that Josephson junctions, the current that you can measure, which is easy to measure, right, is directly connected to the phase, which is a quantum parameter. And then the phase has a very important role. When you see in optics, I'm going to go back to this very simple sketch in optics. When you take monochromatic light, right, to have a single frequency, like we have also with the AC Josephson effect, and you send the light through a small slot, you know that you will observe some dark and light features. You will have a diffraction pattern, right, which is well known. In optics, you call that airy spot, and which limits the resolution of instruments. So if you want to have a good resolution, you need to have a very wide slot, like a large telescope, for instance, if you want to see a star very clearly. And the reason for that is when you calculate the intensity, as you know, the intensity is the square, well, it's more exactly the electric field times the complex conjugate of the electric field. And the electric field is can be considered as a complex quantity, right? Because we are at frequencies 10 to the 14 hertz, where the system doesn't respond instantaneously. You need to take into account complex features. Electron cannot move if you're on a metal, for example, at the speed of the light. And finally, you all know, I'm sure you did, at least you did this calculation someday. You had to calculate the electric field across this place here, and you sum all the electric fields. And the phase here is not the same as here, because as you see, there is a dephasing here between this part of the light and this part. So finally, you do an integral of electric fields exponential I phi, with phi is proportional to this distance between this bottom part and any point across the slot. And when you do that, you get a function which has I don't remember the name of the function in English, but it's a cardinal sinus. It's a sinus x over x, and that's for electric field. And to get intensity, then you need to square it, and then you get this diffraction pattern, which is a sinus x squared divided by x squared. So this is diffraction, right? You have the exact same thing with a squid. A squid is two Josephson junctions, one here, in parallel, right? And they are connected to this wire. So you pass a current here. This current will go here and come back and go there. And the interesting feature is that, of course, here in these two junctions, you have a difference of phase, right? Phi for the first junction, phi in another phase for the second junction. And as you saw before, the phase is connected to the flux. So it means that if you put a magnetic flux external across this loop, you will change the properties of this device. And you can understand that the phase, you can understand this loop as just a superconductor loop with two weak points, right? The barrier are weak points. But in any case, if you forget these weak points, if you have a superconductor loop, if you do one turn, you should have the same phase modulo 2 pi. You cannot have two phases which are random, otherwise it means there is no coherence and you don't have a superconductor. So when you integrate the phase over a loop, you have 2 pi, and 2 pi correspond to flux of phi naught, this quantum h over 2e, this quantum magnetic flux. So, so meaning that if you try to change, of course, you cannot change the flux inside if there is no weak point, if you have no Josephson junction. When it's cooled, there is some flux, which is 1 or 2 or an integer number of flux, but they cannot change if there is no Josephson junction. They are fixed, like when you cool a Josephson junction. If you cool a loop, the flux is fixed. It can be 0, but if it's something else, it will stay something else. You cannot change it at all, unless destroying superconductivity. But if you put these two weak barriers here, they are not superconductors, the barriers they can be insulators. Then you have to have some energy, magnetic energy crossing the barrier, right? And changing inside. And since you need to quantize this loop, to have 2 pi over or 2n pi over this loop, it means that when you change the magnetic field, the system will react to keep this number, this phase difference over one turn, a multiple of 2 pi. And if it changes the phase difference, it means the Josephson junction phase difference will change here and here. And finally, if it happens, it means if the phase is different, the current here will be different, and on both of them. And what you can do is measure the total current as a function of the magnetic flux, and you will see that there is an influence of the magnetic flux, because the system must react to keep this fluxoid quantization, I should say. It means flux quantization, plus this let's say difference of phase, which is associated to a flux, but it's not a geometrical flux, it's a quantum flux in some way. It's something which has the same quantum meaning, but that you cannot really represent by a magnetic field here. So this fluxoid here is quantized, and this is, if you do the equations, if you go to the formalism, like in optics, you have the exact same calculation. Just you replace electric field by wave function, and you replace the phase of the electric field by the phase of the wave function. The good thing is this change of magnetic field here, which changes the phase. It's exactly the same as here, the change of angle. If you change the angle, you change the phase, right, between this point and this point. Here, if you change the magnetic field, you change in the system, so you change the current. So instead of measuring like intensity, here you will measure current, and here instead of changing the angle, you will change the magnetic field. So you should get the same pattern, diffraction pattern, by putting the phase here on this axis, and instead of the angle, and here you will have the current in the squid. And that's, you can understand why it's called a squid. It's a superconducting quantum interference device. You have interferences between two waves in some way, right? Circulating wave functions circulating on this solid state system. So that's a very good property. And also, of course, there is kind of a pun with this word, because, as you know, calamari or squids are often made in a round way. So that's a very nice word, and I think squid now is a word that everybody knows. So, of course, you can do diffraction, but you can do also interferences. Here, maybe I mixed two things. I put two junctions. To have this interference, you need to have two slots, of course, two slots. And this change of phase across the slot is a change of phase across the junction, because the phase is not necessarily the same everywhere if the junction is large, right? So you have diffraction if you have only one junction. You will see this curve. And if you put two in parallel, it's like the the experiment with the two slots, right? Then you will have interference. So how we represent a squid, the DC squid electrically? Well, it's very simple, right? You have these two junctions here, these two, connected by a wire, so it has an inductance. You have the current here. You will measure the voltage across this junction. As I said, there are two junctions. They have a capacitance, each of them. And we also put this normal resistance because even if you don't want, there are some quasi-particles, and at some point, when you put too much current, you will have a resistance. So it means the current will go through this resistance. It corresponds to the to this part, right? That you see. So simple model is to say that this resistance is constant, but there are more evolved model where you say the resistance is nonlinear versus voltage. And you can put that in this electrical model. You put an arrow here. You put it nonlinear to take into account a little bit better the properties of squids. So when you, I just give you an example of a squid that we measured a long time ago, and I like to show it because we see a lot of things about it. It's a very simple squid with two niobium junctions. So you see two niobium ground plane, say. You have an insulator that you don't see, it's transparent, and you have two junctions. These are the two dots here, 1 micrometer diameter, typically. And we have a counter electrode with this structure. Usually to measure the IV curve, you just pass the current here. It goes here, it goes through these two junctions, it crosses the tunneling barriers, and then go back here. And when you do this measurement, you observe this IV curve. It's a screenshot of oscilloscope, as you can see. There were, yes, this IV curve is not maybe the one of exactly this device. I see because here are 4 millivolts, but here there is just one junction. So here there are two junctions in series and two in parallel. But anyway, you see clearly the Josephson current, right? With IC, the maximum current, which is, okay, so this is Cooper pair current. And if you go higher, you will switch here, you see the gap voltage, you see the beginning of the linear part, and you see here, of course, the junction is not perfect. There are some pinholes inside sometimes, or some cross tunneling, which is not quantum tunneling, and you see some leaks here, like a large resistance in parallel. That's like that. A good junction should be better than that, but this one is not too bad already. When you go to the details of this part here, which we did here, if you make a close-up view, if you do, you keep the remanence of the oscilloscope to see the point passing. You do a lot of cycles like that, right? You increase, you decrease the current, and you measure how many times it crosses. You see very interesting features, right? You see that it switches at different quantized values, not anywhere, right? This is one thing I want you to observe. I mean, this is just a simple measurement to do. Right? You just measure voltage on a simple device. And the second thing you can do is apply a magnetic field on this system and measure this maximum current here. And what you observe when you do that, you observe this. It was not a perfect squid, of course. You observe this, right? This critical current, the function of magnetic field. The magnetic field here is in Gauss, so it's about 10 to the minus 3, 5 millitesla. You clearly see some diffraction pattern, right? This is really due to the size of the junction. You can find even the size of the junction from this periodicity. So you have this typical diffraction pattern, not very symmetrical because the device was not perfect. But you see here it's like a bit messy because we didn't take so many points. It looks like a bad measurement. but not really, in fact. If you do a close-up view here on this part, and you see it here, you see what you observe, in fact, is not totally messy. Of course, if you take 1 point out of 20, you will see this kind of thing. You have this sinus or cosinus curve, right? And this is the interference between the two junctions. This is really, you apply the magnetic field, you have interferences, like if you have this two slots experiment, right? And you see exactly. So you have an interference diffraction pattern, and you can observe it very simply by measuring a current and versus a magnetic field that you apply with a small coil, for example. And these lines you see here are simply depending on the magnetic field and depending on the conditions, on the speed of the sweep. It means sometimes the system has a maximum current here, sometimes it has a maximum current here or here, and you see these different levels here, which are a result of these quantum properties. So that's one example. I will go very fast to the equations, but you have an external flux, and the current is just the sum of the two currents when I only consider the magnetic field, the Cooper pairs, right, with the phase of the junction. And the phase of the second junction has this relation because of flux quantization on the loop. And you have this difference, I don't know how we say it in English, the difference of walk difference in optics, which is connected to the phase difference. And you can finally very simply observe that the current has this expression with this sinus of the walk difference and this cosinus of external flux. And this is basically what you can get here with this kind of curve, very simply. So the squid modulation is very important. You can use it for, as you see, it's sensitive to magnetic field. So the first idea which comes is to use as a magnetometer, very simply. So you change the magnetic field or the flux in the loop, and you check how the maximum current changes. So you manage to stay in a zone. You don't have a high magnetic field. You stay in this zone here where it's sensitive, just the top, right? And you make a closer view here, and you stay in this zone, and right. And if you adapt the parameters correctly, it's not the case of this squid, but if you do it correctly with a smaller inductance, a smaller length here, you will get a very nice cosinus or sinus like that. So here you have typically a transducer curve. You can see that you can change the current very fast with a very small change of magnetic field. So the idea is very simple. You can measure the current, for example, and when you change the magnetic field, you have, if you stay in this area, which is linear, don't go there. If you stay in this small area here, 1/3 of about 1/3 amplitude, then simply you can you have a current proportional to the flux. So you have a transducer, a linear transducer, and you have a magnetometer, and very sensitive in terms of magnetic flux. In fact, it's not easy to measure directly the current. It's better to measure the voltage, but you can do it the same because the IV curve, okay, here the voltage is vertical, but basically you have the Josephson current here, and this curve is a bit, you have the nonlinear part here, and you go to the normal resistance. And if you apply, if you have no magnetic field, you have this curve here, or an integral number of magnetic flux. You have this curve, and if you put half a flux in the loop, the system will react, and it's a worst situation for the change. And the IV, so you will have different current in the two bunches, and then you have a different, you see a different IV curve. So instead of measuring the change of current, what we do usually is we bias. We give a constant current. We go this way, vertical. We put, for example, here. And when you have a magnetic field changing, the voltage is changing, and you just measure the voltage here, right? And you have this periodicity with phi naught. You will see this voltage going up and down. So if you are here, you go from 0, and sometimes you go there on this vertical from here to here. So you have optimum, right? You need to place yourself where the difference is highest to have the biggest change, to be more sensitive to the voltage measurement. If you come here, of course, it's nearly flat, you don't see any difference. But you bias it typically here a little bit above IC, and then you will have a good transducer. I have a question about from Marty Gutierrez saying, does the current with verse field curve in slide 10 imply that at larger fields the squid modulation decreases with increasing absolute field? I'm going to go to slide 10. Maybe I'm not sure it was a 10, but maybe this one. Of course, you need to manage your squid to be with the right parameters. If you don't calculate, you will not be optimized. And you don't want to be in this area where you have a low amplitude. You want to stay to the maximum. By the way, you see the maximum here is not for 0 field. It means when I cool this device, there was some magnetic field, the Earth's magnetic field, basically, and it was trapped in the loop when it became superconducting. That's why I have a maximum here, which is not for 0 field. But anyway, so you want to be in this area, only in the maximum, so you avoid to have flux trapping. And in fact, with a good squid, you will have a small loop here, so you cannot have many fluxons. You can have only one. So you will not see all these details. You stay here, and then you will have the good properties to have the best modulation. Otherwise, yes, the modulation decreases. Okay, so I was there. Asymmetric case, I'm not going to detail everything, but of course, if the two junctions are not the same, you have these modulation curves are not symmetric. And you can also, it's also a way to measure asymmetry of fabrication, for example, or you can use it as well as a way to measure specific things. And another parameter which is very important, I didn't talk about it, but this is beta L, we call it beta L. It's a product of a critical current by the inductance of the squid, right? The inductance of the wires, finally, which connect the two junctions. And you want to have this beta L not too high, right? Usually below 1 or much below 1. And you see how modulation happens depending on beta L. In my case, on the curve I showed you, where you had these yellow curves, right, on the oscilloscope, I had a beta L very high. So the modulation was not very good. That's why it was difficult to see. But it was not a squid made for magnetometers. If you want to make a magnetometers, you make a much smaller inductance, so L will go down, beta L will go down, then you will have a stronger modulation. And as well, you will have only one solution. You can have one flux or 0. In my case, if you have beta L, which are a multiple number of finite, then you can have several possible states. And that's where what we saw also on the IV curve with the different changes. You have different configuration. The squid can trap one flux or 2 flux or 3 flux, and you don't know, in fact, in which state it is. You don't control it, at least, and it can be a problem. So you avoid to be in this case. And here is a curve where measured, right, with all the good properties of the squid, where you can really see diffraction by the junction. It will give you the information about the size of the junction, basically, and the interference between the two junctions of the squid, right, with this diffraction term, which is this envelope here, and interference term, which is all what you see. Oh, we don't use it, of course, like that. We just keep this part to be, we even keep, yes, just a small window here to measure the difference of magnetic field. And of course, This is why it's sensitive. You have a very high change over a very small variation of magnetic field. So the energy resolution of a squid, it has been shown by a paper of Tesche and Clark, which is very well known. You'll find that in the handbook of Clark and Baginski. The energy resolution is given by this formula. It's necessarily higher than h bar over 2, and you know why. And you see that you have a good energy resolution or magnetic field resolution if you have a low temperature, of course, but also the capacitance should be low and the inductance should be low enough. So you need to control these parameters. That's our optimum parameters. They are optimum parameters to design the squids. And to make it, to use it in a simple way, you use, I say you bias in current, and then you have a variation of voltage. If you leave the squid loose, it will be complicated to manage because it won't be accurate enough. So the way we do that in electronics, if you want to have a good measurement, you know that you need to constrain your system, and you make a phase lock loop to keep the voltage constant, and you measure the reaction in you measure the quantity. Here the current in the feedback loop with the information about the voltage. Here it's the same, except of doing a phase lock, you do a flux loop. So you have the voltage here, it appears through this inductance, it's converted magnetically with an amplifier, you have a locking detector, an integrator, and then you have, if the voltage changes, you react, you apply an opposite flux to keep the flux constant here. And you measure the current in this feedback loop, and this current in the feedback loop is a perfect linear image of the voltage here, which depends on the flux here, then of the feedback flux, which compensates the flux, the external flux you want to measure. That's the way it works. Okay, and well, I will not go to the details of all these flux modulations, but you can also, for the locking techniques, you need to do flux modulation to remove noise, and in particular, and to be more sensitive. And of course, if you can do magnetometer, you can do gradiometers. Magnetometers are good to measure the field which are far away, but sometimes you want to avoid the constant local field, the Earth field, for example. Then you measure gradients, spatial gradients. So you can do axial squids or planar squids. You can do in series, in parallel. You have all kinds of ways to do gradiometers. And yeah, these are examples that you can find in a book of a paper of John Clark to make first, second, third order magnetometers, even sometimes. Here it's second order. Gradiometers in one direction here, this one, of course, vertical. How they are fabricated? Well, you can see how they can be made. You have here some multi-channel gradiometers with all these squids, which are in a non-metallic system, and they are attached at the end of a dipstick, and you just plunge them in helium, liquid helium. And then, of course, outside you have all the electronics at room temperature to extract the magnetic field gradients. The way it's done with planar squids for, you see the squid here with the two junctions. If you want to be sensitive, you need to have a big loop, a large loop, to capture a bigger magnetic field. But if you have a larger loop, the problem is you have a larger inductance. And that you don't want, because then, as I said, the energy resolution will not be as good. So what you do is transformers. Basically, you do transformers. So here you have a low inductance because it's a thick plate. You know, we call it a washer. It has a low inductance. You have the insulator here, and on top of that, you deposit a spiral coil. This one has a high inductance. This one can capture a lot of field, and it will focus it inside this low inductance. So you have a flux transformer, like you can have a voltage transformer in AC electricity, and it's a way to do, let's say, a flux impedance match between the device, which is here, the two junctions, and the external magnetic field. So all kind of techniques to develop good squid. It's really a work of specialists. And here are examples of, we don't see too much of the washer here, but we see at least the spiral, and you can see here the junctions, so which are here with some parts of the in part of the washer. Okay, and you can do, of course, three-axis magnetometers by putting 3 chips on a cube, how we could say, a corner cube, right? And there are different techniques as well. You see here, we call it a wheel. There are different inductances in parallel, in fact, to reduce the inductance to improve the sensitivity. So all kind of engineering techniques, say. Another kind of a squid here on a chip made in Germany at in the University of Vienna. And I think that's about it for this part. I would suggest that we take a break. I take a break because it's live, maybe a 10-minute break. You have a source of knowledge here that when you have a lot of good references about squids and skiffs. Skiffs, it's quantum interference filters. Skiffs is the equivalent in optics of grating, right? When you know to do, you take 2 slots, you can do a large number of slots to have a grating, and you know it's a good way to do spectroscopy, to select some wavelengths. Well, you can do the same with magnetic field, with the squids, and then you will select magnetic field in a much better way. And so these skiffs are also used for different applications, like magnetic antennas, so where you can be very sensitive to the magnetic field in some area. So I will not talk about that, but you have all these references where you can get a lot of hints about these squids and skiffs. And I think here I have a slide which is not coming, but at least on my part. Oh yes, so that's digital electronics. So I suggest that we make a break if it's possible. I'm asking the technical team if we can. Yes, okay. So what I suggest, we take yes, 10-minute breaks, and then if some people have some questions, they can prepare them, and I will answer about the questions on squids just when I come back in 10 minutes. And after we'll do the last part about digital electronics. Okay, welcome back. I hope the break was long enough. It's a long day for you to listen. I'm quite sure it's a lot of things. First, I will answer 2 questions have been asked, which have been asked. The first one is by Marty Gutierrez about the inductance of spiral coils. Are they comparable to that of a closed coil? In fact, we use spiral coils because you can have, for the same area on the chip, an inductance which is not exactly equal to the number of turns, but nearly, right? So it's basically about the same as a solenoid, just the geometry is slightly different, so you need to calculate it specifically. But that's the reason why we do that. Otherwise, we would need to have a much larger coil, and it would take a lot of space on microelectronic chips with nothing in it, right? So the cost is connected to the area. So usually it's better to have smaller chips, like 1 centimeter, sometimes 2 centimeters square maximum, and then you do a multi-loop. That's the reason. Then you have an inductance which is multiplied by the number of turns squared, and then it's how to say, then you have a larger flux, right? So you are more sensitive, in fact. The second question was by Alessandro Reineri. If the flux locked loop effectively applied as a phase locked loop equivalent in superconducting based microprocessor electronics. So what I can say is this flux locked loop is in fact a classical electronic phase lock electronic. We just, instead of reacting directly on the voltage of a signal which would shift, and then there would be a phase shift, right? We do it directly with a flux where we measure the voltage which is connected to the flux. So it's exactly the same technique. It's a room temperature electronic, and there is nothing special about it. In superconductor microprocessor and electronics, they usually the only, how to say, we do this flux loop, these feedback loops externally. Otherwise, if you want to do it at very high frequency, if you want to run a system at 50 gigahertz, indeed, you are obliged to do a flux loop with superconducting electronics, and then it's really a specific design based on Josephson junction. It can be made like mimicking semiconductor electronics with digital functions, say, or analog functions. But the other way is to do it by using the physics of the Josephson junctions, by writing directly on more complex circuits. These phase lock loop are, for example, used for high frequency receivers, where you need to keep you have some noise due to the Josephson junctions, and you need to keep the current constant, and that you need to do directly with Josephson electronics. So it's a specific design in this case. The principle is the same in terms of, let's say, the electrical and mathematical theory is the same, just the way to do it is a bit different. Then, okay, if there are no other questions, or you can continue to ask your question in any case, I will continue with the third part of this short course, which is about digital electronics, which is now more under development, and which becomes major. And I think it's important to understand how we do digital electronics today, because as you know, with semiconductor, digital electronic has changed everything. And I'm quite sure for superconductor electronic, digital electronic will also change a lot of things, especially at microwave frequencies, where you can make a simpler system, cheaper, more flexible, which we cannot do now. When in radio astronomy, when you do an instrument, it has only 1 pixel, 10 pixels in the maximum, and it's really very expensive, very complicated, with a lot of analog electronics and costly parts. So we need to go to digital and put everything on a single chip, cooled at 4 Kelvin, and that's really a lot of. There is a lot of hope to have that, and to do the same as we do with semiconductor electronics, but at much higher frequencies in the, let's say, at least 100 gigahertz range, and even half a terahertz. So I'm going to explain how it works mostly, and a little bit of the history. So the history about digital electronics is really from Moscow. Moscow State University, by Konstantin Mikhaev and his team, and working on the physics of Josephson junctions. They understood quite some of the things. You can see all of it in this book by Konstantin Mikhaev. And the history of in fact of this logic was to mimic semiconductors. Very simple. You see the IV curve with I'm not talking about purely Josephson current, Cooper pair currents, but about the full IV curve of the Josephson junction, where you have 2 branches, right? One at 0 voltage, which is a Cooper pair current. If the voltage is 0, we could call that in logic, binary logic, 0 state. And if you are at the gap voltage, you have a more quasi-particle currents, and you can call that state 1, right? So you have two levels clearly, and if you can switch between these two levels, you can make what we call a static logic. It has been developed in the 1980s with IBM, and also in Japan with MIT for a long time. So they succeeded to make it work, but it was not very high frequency, just a few gigahertz. They needed to cool at 4 Kelvin at this time, which is of course not very appealing for consumer electronics, right? And also the technology was not mature at this time. Niobium was not developed yet, Niobium technology. It was mostly lead technology, with superconductor was lead. And the problem with this material is that when you cool it, it becomes superconductors, but when you make a thermal cycle, you stop it and you cool it again, the junction had different properties. It was not stable at all for physical-chemistry reasons. And then it was like really jewelry and very complicated to get this working. But it worked up to a few gigahertz. It was limited by what we call the punch-through effect. On this IV curve, you see the positive part of the voltage, but it's symmetric, right? You have the negative part here, anti-symmetric, sorry. And then sometimes when you want to go back to 0, you go to -1, right? It was a bit complicated to manage, let's say, the dynamic of the charges and the voltage. So it was a limit. And yeah, then you had to cool. So there has been a lot of development, and some of these books that I mentioned before, really all the knowledge of superconducting electronics comes from this period where there has been a lot of investment. The objectives, primary objectives were not maybe totally reached, but a lot of things has been achieved and which we use now. And we may have the same situation with quantum. You know, now there is a lot of funding for quantum computers. We don't know if there'll be one quantum computers, but at least there'll be a lot of developments and a lot of understanding about all things about the quantum, around the quantum field, and that will probably be a big step for knowledge and future applications, which may be different from what we imagine today. But anyway, so after this happened, mostly in the United States and Japan, the team of Konstantin Likarev understood that there was, it didn't work very well because we mimicked semiconductors, basically, with these two states. And the history has shown that every time with superconductors, you mimic semiconductors, you fail. One of the reasons I think is that the fundamental physics behind semiconductors and superconductors is not the same, right? Semiconductors are based on electrons or on fermions. They follow certain statistics, they have certain properties. Superconductors are based on Cooper pairs and bosons, and it's totally different. So if you use a system in a mode which is not his natural mode, it will not be very good, right? If you are not very good at, I don't know, at running fast, you shouldn't do this job of running fast. I mean, try to go in a field where you feel at ease and you have natural good properties, I would say. And it's the same for superconductors. And what has been understood by Likarev is that we shouldn't use a static logic with these two states, 0 and 1, because it's slow. It's slow to go from here to here and to come back at the right place and not in -1 state. And he proposed a dynamic logic, which is really relying fundamentally on the physics of Josephson junction. This is what we're going to see now. So to understand that, you need to come back to the Josephson junction IV curve with its simple model. Yes, there was an animation, but anyway, the junction is behind here, it's across. You have the capacitance and you have the resistance here. and so you have the current goes in three branches, right? Capacitive current, Josephson junction current, and the resistive current. To the first order, we can say this is quasi-particle, this is Cooper pairs, and this is displacement currents. With the three equations that you can see here, Ohm's law, this one you know as well, I'm sure, and this one is the first Josephson relation that we saw before. The second Josephson equation, I told you it was Faraday's law, it is there. So you have a very simple electrical system to solve. And when you solve that, when you see you put the phase, you have it here, you can derive the phase from this equation, put it in this term. You get something like the voltage is an inductance times the derivative of current versus time. And this inductance is here, is Lj Z naught divided by cos phi. It's nonlinear. It's nonlinear. We call it, so the linear part here, we call it the Josephson inductance, phi naught again, over 2 pi IC. So this is it means with these two Josephson equations, you can model a Josephson junction electrically with these simple models at least as nonlinear inductance. That's why I put it here. And of course, if you keep the phase very low, or in a place where the cosinus is about constant, right? It means with a phase of 0 when the cosinus is 1, you have something nearly linear, right? And then you have a RLC circuit, parallel RLC circuit. It's a simple circuit, right? It's the first thing you study at university in electricity. You have, you know, to solve this kind of system, RLC circuit, and it's simple to solve. And now we will see the properties. But of course, what makes it difficult is in the general case, the phase is not constant. Then it's nonlinear, and then it gets quite complicated, I must say. And then it's not always obvious to understand how it goes. There are some ways to do it, but okay, I'll show you a little bit about that. So when you have an RLC circuit, you have, when you put the differential equation, you have the normal terms, second order differential equation, but with this nonlinear part, which makes all the good properties of this circuit, but also all the difficulties. So it's an anharmonic oscillator. When you have an harmonic oscillator or harmonic oscillator as well, you have three parameters. Here I have electrical and physical approach. So you can, depending on what you prefer, you can check with electrical or physical parameters. Electrical approach, it's quite obvious. You have a plasma resonance frequency, plasma frequency 1 over square root of LC, which is plasma frequency of the oscillator. You have LR time constant, which is basically the time you need to recombine quasi-particles into pairs, because quasi-particles go there and pairs go there, to make it simple. And so since you have an inductance, it takes time to recombine these electrons equal particle in Cooper pairs, and this is modeled by an inductance in an LR time constant. And you have the classical RC time constant of low pass filters that appear every time you have a resistance in parallel with a capacitor. This is not connected even to the junction, right? It's, well, partly to the junction through the barrier, and geometry. It's mostly connected to the geometry of the junction. So you have this three time constant. You can replace these values by physical parameters. The capacitance is connected to the area, for example. The inductance, as you saw before, the inductance was connected to the critical current. And the critical current is proportional to the area of the junction, right? It's a critical current density in ampere per centimeter square, for example, times the area. So you can simplify this equation, and you see that you have this plasma period, which depends only on physical constant, quantum fundamental constant, so that's simple, and two parameters which are really a property of the barrier of the junction. You have the specific capacitance. The specific capacitance of the junction depends on the barrier, what dielectric constant mostly, what is the density of the barrier, etc. So this is really a material issue. When you have fabricated a junction, this CS is fixed and there is nothing you can do. And it's the same for JC. JC is a critical current density. And the thinner the barrier, the more you can have tunneling current. So this tunneling current depends on the barrier, on the thickness of the barrier, and also, of course, on the nature of the barrier, depending how the particle can cross this barrier. So we see a constant which depends on the material, on the barrier, a material barrier, and of course also on the material. It's the same for RC. RC time constant. If you calculate, you have the gap energy. The gap energy is connected to the material, right? If you have niobium, you have 2.8 millielectron volt for this VG. If you have aluminium, it will be 0.3. So it's a physical constant. There is nothing you can do. And once you chose superconductor, and again, you find these two parameters connected to the barrier. And the Taylor time constant, this one, you see, doesn't depend on the barrier. It only depends on the material. Fundamental constant and gap energy. It means you can calculate this value for niobium nitride, for aluminum, for whatever. This is something intrinsic to the superconductor material. And as you see, this is a value which is very low. For niobium, it's 0.15 picosecond. So 1 picosecond is, in terms of frequency, is 1 terahertz. And then it means you are already, you see, at 10 or 15 terahertz. You can go very fast. So there is no limit on the speed due to these parameters are connected to this, I'd say, microscopic physics and the way particles, quasi-particles and Cooper pairs interact. But these two parameters you have control. This ratio is important. So when the first thing to do is to linearize the equation to at least try to understand what happens if you have a simple system. So you have a classical RLC circuit, you can calculate the damping coefficient, you can calculate the quality factor, and you know that for a damp oscillatory regime, transients evolve as exponential of minus t over 2 tau RC. That's just basic physics of RLC circuits. So I did the calculation for a junction that I used a long time ago in radio astronomy. This is ohm. It looks like in weight, but it's so this junction was fabricated. It was a bit like the one I showed you in the squid. You have 12 ohm of normal resistance measured, 190 femtofarad of capacitance that we know about. There are ways to do this measurement. And critical current you measure on the IV curve. It was 200 microamp. You see the IV curve here, right? It's an experimental one. There is no Josephson current here. It has been suppressed by a magnetic field. Like with the diffraction pattern, you know that when you put a magnetic field at some value, you don't have any more current. It's like dark light on the optics experiment. So we did that to remove Josephson current. So you only have quasi-particle. And so we can calculate this time constant, and you can see that the time constant, the two time constants which poses problems are this one, 2 RC and 2 plasma, about 2 picoseconds. So 2 picoseconds is not too bad, right? You can still go fast with 2 picoseconds, is 500 gigahertz. But now let's see what happens when you want to bias the device. For example, you are at 0, you want to bias it at 50 microamp. So you will stay on this branch because you are not above IC of the Josephson Cooper pair critical current. And we tried also another point at 300 microamp above IC to see what happens. If you use 50 microamp and you check the dynamics. You can put that in a solver, in Spice or whatever. You can calculate the dynamics and see how the current and even the voltage of the junction moves with time if you apply this current suddenly. And you see that with 50 microamp, you will see that. Okay, so the voltage will change because since you change the current, you change the magnetic field, Faraday's law applied, you have a voltage, but there will be an oscillation and it will go back to zero. So you see the average is zero. There is a variation of current, of voltage, sorry, but the average is zero. So on the oscilloscope, you see nothing. That's why you are on this vertical branch, but it doesn't mean there is no voltage. What you see is there is no average voltage. At high frequency, you have a voltage, and this high frequency is connected to the Josephson frequency. You remember, about 500 gigahertz for 1 volt. So it's very fast. You cannot see it. Even if you had a fast oscilloscope, you couldn't see this variation. You see a period is about 4 picoseconds. I mean, it's 200 gigahertz. There is no oscilloscope checking that. Okay, so you have this variation. And if you want to go there, to do this latching logic, right? I'm at 0 state, I want to go to 1 state, I will polarize there. Then when you solve the equation, you have this linear part here, which when you have, you remove the sinus. And when you put the sinus, you will have that with this whole oscillations here. So what is important here is, for me, 0 voltage is 0 state, and this voltage here is 1 state. Right, it's a state 1. So I can do logic. I go from 0 to 1, and then I come back 1 to 0, and I can do a logic operation. What you clearly see here is, if to be sure you are at 1, you need to wait a little bit of time that the system comes here, and you see this is slow. In fact, tau RC is 2 picoseconds. You need 6 tau RC about to be at the maximum. And then the same quantity to come back. So you need 12 tau RC, basically, about, to go from 0 to 1 to 0. So you see 12 tau RC, it's already 23 picoseconds, even more, right? 25, 26 picoseconds. So you're already at 1 terahertz divided by 25, right? So it's already much, much slower. It's still a few tenths of gigahertz, but still quite slower than what we could expect. And the reason for that is you have this resistor in parallel. You cannot get rid of it. And the capacitor as well is very important. It's a problem. And so that's the only way to do static logic, and it's slow. It's slow. That's one of the problems. So how to get rid of this problem? Well, the only way is this constant here is very slow. So the way would be to reduce R or C, because it's a product, right? To RC is R times C. If you reduce, it's difficult to reduce the capacitance because you cannot change the material. At least today, we are not yet mature enough in terms of technological development to choose a barrier and have a very low capacitance barrier. But I can tell you, if you can find a material with a very low capacitance compatible with superconductors, we will make a big jump in improvement of technology. Material studies should be really essential now for new barriers, to do barrier engineering. But for the moment, we have what we have. This C you cannot change really. Usually it's aluminum oxide or MgO, but they are not very good. So the only way is to reduce the resistance, to reduce tau. So it's easy because you just shunt. That's why before I showed you a resistance in parallel with the junction. You shunt the junction with a small resistance. A normal resistance, you put a molybdenum or well, material that you are used to in microelectronics clean rooms. And then you can reduce the resistance. And what you see by doing that, if I come back to this this RC time constant, is that if you reduce R, you will reduce to RC. But since you do artificially increase this by putting another resistor in parallel, you will increase this one. So you cannot reduce as much as you want. You have a trade-off, right? You have a trade-off. So we are going to see what's going to come from this trade-off. I'm checking. There is still a question of Marty Gutierrez on the squids. Are spiral coils compatible with flux transformers? Yes, yes. Usually we use spiral coils in flux transformers. They are usually done like that. Right? It's a way to change the ratio. And so there are different ways to do the transformer. If you do DC transformer, you really have your squid is just connected to a spiral, right? Both ends of the spiral to the squid, and you take another coil going to the electronics. It's a way to do it. So there is nothing. Both are really connected on a circuit, and they are closed circuit. But you can also do it in RF way, and then the spirals are not necessarily closed. They can be open, and then you have a resonance. You need to think only in terms of AC signals, and then it can do the same as well. Okay, so from reducing the capacitance, I told you if you want to reduce the switching time, you will reduce the RC time constant. Then the only way is to reduce R. There is a problem with the slide, but anyway, because C you cannot do. If you calculate with the state-of-the-art technology what frequencies you can get with the static logic, today we are more at 10 kiloamp per centimeter square as a well-mastered technology. Sorry. There are some foundries doing some junction at 20, but you see with niobium, which is this curve, that the frequency will go to a maximum of about 40 gigahertz, maybe 50. This is theory. Practice will be much lower, and it's today. You can imagine in the 80s, we were more there, and the maximum was 8 gigahertz. So it's faster than semiconductor, but not so much. And you need to cool at 4K, so you cannot really compete super semiconductors with that. But if you reduce, as I said, if you reduce this R, then you will increase a little bit this one. You have a trade-off, and the trade-off is when these two values are the same. So basically, you take a parameter, which is a ratio of tau RC over tau LR, and it has this expression, right? And it's called the Macomber parameter. You will see this parameter a lot in the books. This is a typical parameter to understand the dynamics of Josephson junctions. And this Macomber parameter should be 1, right? It's optimum. Otherwise, either one time constant or the other one is too large. So if you do that, you can recalculate, you have a relation between these two values, and of course this one as well. You can recalculate the new time constant, and you can find that it has this value. It's connected to phi naught, this famous quantum magnetic flux, and to our shunt IC, which is really the parameter you need to maximize to minimize time constant, right? And that is a technology related issue because you cannot do what you want here. And then the criteria, we can show theoretically that if you process this equation again, the criteria for the maximum frequency is 1 over 2 pi tau naught, 2 pi times this one. So it's not exactly 1 over 12, it's 1 over 6. And basically the maximum frequency is around 500 times this critical voltage, R shunt times IC. And this maximum frequency is much higher now. I have a curve here. If you take niobium, for example, with the current state of the art, 10 or 20, you get about 300, 400 gigahertz, right? It's what you can reach reasonably. In practice, you are lower, typically the 1/3 of that. So you can find today a digital circuit with 100 gigahertz clock frequency. You won't go much further away with niobium. We will reach the limit soon. It's still not yet reached, but very soon, I'm sure 5 years from now, we will need to find something else. Niobium nitride is a bit better, but it has other problems. It's also an alternative. And probably we need to go to more, and I think it's the job of next generations of physicists and engineers and applied superconductivity people to work on that, to engineer new materials, new barriers to overcome this, and we should reach, I think our goal should be to reach 1 terahertz of clock frequency. So superconductors are really unbeatable from any other technology. There's still some work to reach this point. Also, we need to increase, of course, temperature of operation and increase TC, but it's not as critical. You'll see why. So when you do that, when you shunt the junction, if it's not shunted like the junction I showed you before, you have mostly this curve with the Josephson branch and this quasi-particle branch. Beta C, which is a Macomber parameter, is very high in this case when you don't shunt the junction because R is high. It's a normal resistance, and you see beta C is proportional to the resistance, normal resistance squared. This one you cannot change. And if you reduce, you shunt the junction, the IV curve will change. You have a big hysteresis here. It will become smaller. When you reach beta C of about 1, you don't have any more hysteresis. You can simulate, you will see the hysteresis disappears. And if you have a very low beta C, low resistance, I showed you IV curves before, you get directly with non-hysteretic junctions. Here are some pictures of curves that I measured a long time ago. I didn't change beta C, the resistance, because it's not easy to do, because it would be different devices, but I just changed the temperature. You can show that the normal resistance will change. You can do nearly the same. You can reduce the beta by increasing the physical temperature. So you see the normal IV curve with the hysteresis here, with beta C higher than 1. When you reach 1, you have a little hysteresis here. And when you are below 1, you see the curve is totally different. So now these junctions here, beta C of 1, they are very, with the dynamic shows they are very fast. The problem is you don't have any more 0 state and 1 state. You just have one monotonous IV curve. So how can you use that to do logic systems? And this is where the Likaev got this great idea about the quantum and dynamic logic. But in any case, I showed you again these curves where you have a simple junction without shunt. You see the hysteresis and you take a shunt and you see how the IV curve is modified. So what's happening now? To understand what's happening and why we don't have any more hysteresis, you need to resimulate the same junction and put a shunt resistor in parallel. So it's a simple electric circuit, right? You shunt it and you recalculate. You check the dynamics when you put a current. And what you see is, of course, I did with sinus phi, not just phi. You have, of course, this same curve as before for this one. This is a junction which is not shunted, all right? You have this small oscillation. And when you shunt it with beta C was 1, here beta C was 17, right? With the parameters of my junction. It's a real junction I used. And when I put by the calculation a beta C of 1, this constant is 0.56 picoseconds, so it's fast, right? 500 gigahertz should go fast. When you see the dynamics of it, when you check how the voltage evolves with time, it's very strange, right? It's not just a constant level. It's like these bumps here. You see these bumps are bigger than here. And, well, you cannot say it's constant. It oscillates. And here is all the physics of Josephson junction behind that. These oscillations are the Josephson oscillation at this 484 gigahertz per millivolt. And here as well, in fact. And if you remember this equation of differential equation with the sinus phi. You can check just on the equation. If you change phi by 2 pi, right, you will get the same equation. But when you do that, if you change by 2 pi, you see that the voltage will change by phi naught. If you integrate the voltage from the Josephson equation. It means when I change the phase by 2 pi, I have the same equation, so you should have the same current. I can, for example, take the 2 point A and B here, and the voltage integral, it means the area under this curve here, is phi naught, it's quantized, basically. So every time you have an oscillation, you have one flux quantum passing. I'd like to remember that a flux quantum, a flux, it's phi is Li, right? It's a product of an inductance by current. You can understand if you take a loop, a closed loop of inductance L, and you have a current running, the flux in the loop is L times I, right? But if you can also see the flux differently by saying that the flux, you use Faraday's laws to understand that, the flux, it's also the integral of voltage over time. So it's a product of a voltage by a time, right? And in this case, you have your flux moving. It's moving, it is changing, and this is the area under this curve. So you have one flux passing here, and here as well, in fact, you have also one flux, right? So if you can do a logic where you count this flux, and you say when there is one flux passing, I say it's a 1, and when there is no flux, I say it's a 0, you have also a binary logic, as long as you are able to manipulate this curve. Here, it's much more difficult to do that. There are also fluxes, but you see, you need to measure a very small difference of voltage to know if one flux has passed. And this is really difficult. I mean, you are in the microvolt and in the terahertz range, it's very difficult. Here, it's easier. You have higher voltages, not very high, right? 500 microvolt, but still you can measure that. And you have times which are reasonable. So and so this is the idea of IKRF, is to use the natural evolution of these junctions to count this flux. So it's a dynamic logic in some way, right? You need to have some oscillations. And of course, if you check an IV curve, you don't see anything, right? You have a monotonous IV curve, you don't see this variation because what you see is an average, in fact. But this average, here, this point here hides a lot of things. If you place yourself here, you would check the voltage. If you were able to measure it, you would see this variation over time at a frequency which is exactly proportional to the voltage. So you have, finally, you have a clock, right? You have a clock. I bias this junction here, and depending on the current or the voltage, I have a frequency which is different. Then I have a clock at different frequency. It's a clock at very high frequency, a few hundred gigahertz, but it's the simplest clock to what you can do, right? You take a device, you put a constant current, and you have a voltage oscillating in a way which is quantum accurate, because behind this Josephson frequency is quantum physics, and you have a frequency which is proportional to the voltage. So it's a very appealing technology to do that, and it can go naturally very fast. But you cannot think anymore in terms of constant voltage like here and here. You need to think different. So that's how we will use it. And to illustrate this, you can, for example, over time, check how is the dynamic, depending on the voltage you apply or the current you apply to the junction when it's shunted, right? Either if I bias it just above IC here, okay, voltage nearly 0, but not 0, or if I increase a little bit the voltage to come in this area, you need to stay in the nonlinear area. Here it's not interesting, you cannot do anything, it's too fast. And what you see is that if you put a current which is just 20% above IC, you have this beautiful curve. If you increase the current 3 times IC, you have nearly a sinusoidal current, as you can see. And if you put 5 IC, it's higher. So there are several things you should notice here. Ah, microphone is okay. Ah, okay. Maybe it was a problem with the network. Okay. Okay, thank you. Well, in any case, I will repeat a little bit myself. So you see here, when you change the current, usually we bias the junction. It's a low impedance system, so you need to bias with current. You can control it very well. You will change the voltage. If you change the voltage, you will change the frequency. And as you can see, the higher the current, the higher the voltage, and of course, the higher the frequency. You see it very clearly here. The higher the current, the higher the voltage, average voltage, DC voltage, this is here, and the higher the frequency. And this frequency is proportional to this average voltage. The interesting thing to see is that, okay, here is very difficult to use that in this range. It's like you use a sinusoidal signal as a clock. And you say, the top of the sinus is 1, and this is 0. 1, 0, 1, 0. You can do that, but it's very difficult because there is nothing you can do in between, right? You don't have the time to do a digital operation like additions or gate, AND gate. It's too fast. But if you reduce the current and the voltage, you go in this area, you see finally that this sinusoidal signal, it is just like this pulse here that you make closer to each other. So the sinus is a limit of this function where you bring this maximum close to each other. And as it's periodic, you can again find that between under each pulse, the voltage, integrated voltage, you have one magnetic flux, phi naught, which is h over 2e. So this is a nice clock, this one, because if you reduce the current still a little bit, you can keep this 0 part long enough so you can do something. I mean, electronically, you can do some functions. So this is a dynamic logic. This is this quantum flux. It's really the vector of the bit information, right? When you count the flux quanta, if you have 1, it means okay, it's a 1. If there is nothing during a time interval, it's 0. Very simple. Okay, so how now we use it? At least what we can do here easily is to fabricate a clock. You take one junction, you bias it just above IC, and you have a clock. Very simple. You cannot do a simpler clock than this one, right? One device. And now how to use it? So these are simulations. First, I can show you some simulations drawn when you take the capacitance into account. What I showed before, I made some assumption. I remove the capacitance because then I can solve analytically the equations. But in the general case, you can't. You need a computer. So you put everything in a SPICE model. You calculate, and you see this clock finally. Well, I told you already about that. The problem we have now, we have a clock. It's good for logic, but we need to manage single pulses to do operation, right? You want to do gates or gate and gates, and you are with this IV curve, which is not, which is monotonous. There is no 1 and 0 here. The only thing we can say is that if you have a small pulse, current pulse here, you will have a big pulse voltage here. This is what you want, in fact, right? So if you are able to have single pulses, you will have single pulse voltage, single flux, quantum single flux electronics in some way, and then you can start doing operation. But still, you need to be able to take this one, which appears just one, not a train of ones, and then you need to stop it somewhere to do something. So you need to store this information, this one. And as this information is a quantum flux, as I told you, a quantum flux, it can also be a current in a loop, in a closed loop. So the idea is you can have a pulse voltage. Of course, a pulse voltage will propagate along the line at the speed of light. This is one good property of bosons and photons. They go at the speed of light. And a big difference with semiconductor. you have a circuit which is able to work at the speed of light on your chip, on your physical chip. So it's fast. It's a chip of light, a guided speed of light, of course. So it's not exactly the speed of light in vacuum. It's 1/3 of it, but still it's very fast. And okay, this one will travel with somewhere in the circuit, and then you need to block it to put it in a small loop as a permanent current. And if you have, and your one will be in this loop, and this is your information, which is stored, and you can try to make it go again somewhere else when you need. This is this is this digital electronic, how it works. This what we call single flux quantum electronic, SFQ electronics, if you prefer, where you manipulate this quanta of magnetic flux. So, so how we do that? The problem is to have one pulse only, and not a train. So we do that in a very simple way. We take a Josephson junction, which is electrical model, and I just short circuit it with an inductance. But in some way, I make a loop, right? Here it's a loop. It's like a squid. It looks like a squid. In fact, it is a squid, except that in this loop, instead of having one junction, I just have, instead of having two junctions, one here, I have just one. But it's also a squid. It's a quantum interference device. When you do one turn, you still, the phase should change by 2n pi, right? But as you see, as it's short circuit, this is not an idea you would have with a normal metal or a semiconductor, right? If you take a device and you short circuit it, it's a wire. It's useless, totally useless. Not with superconductors. It's not just a simple wire. It has a lot of good quantum properties, and it's not stupid to short circuit a superconducting device with a superconducting wire. Of course, you cannot see a DC voltage. It's short-circuited. You have no DC voltage, but you have a phase, difference of phase. And if you can manage a phase by measuring the field, for a magnetic field, you have an electronic, what we can call the phase electronics, right? Quantum phase electronics. And it can do a lot of very fancy things that are not yet studied totally today. And well, probably some of you will go in these fields, I hope, to do new devices based on phase electronics and not just this voltage electronics. So you take this wire that you short circuit your device, and you can still apply Kirchhoff's law. Kirchhoff's law, you know, it's a conservation of energy and conservation of charge. It's still true in quantum physics. So you have the nodal rule. You need to check that the current is the same in these two branches. If you do the sum of the voltage around it loop, it's 0. So the problem with this rule with superconductors, it's still true, but just it's useless, right? 0 plus 0 is 0. It's true, definitely, but it's useless. The good thing about that is if you integrate this equation, right? I just integrate 0. Why not? I integrate 0 on both sides, and I get a constant, not 0. I get a constant, which is not necessarily 0. But when I integrate a voltage over time, I have a phase, right? And the sum of these phases, and you see this is the flux. The flux is connected to the phase, I told you before. It means the sum of the phases are a constant. And if you solve this equation, it's not very complicated. You will see that the sum of the phases is 2n pi. I told you that before. If you do the one turn, you should find 2n pi, otherwise it has no physical meaning. So in some ways, this is a modified Kirchhoff's law, which we can call the law of phases. And then we can consider that the Kirchhoff law is just a particular case of this law of phases for normal metal. So when you solve that, you can. I'm not going to go to all the details, but you can find. You can calculate the external phase. You can define an external phase, which is, I would say, the phase between these 2 points as a function of the phase of the Josephson junction. And you get this relation, which is not complicated to obtain. And so phi is the phase of the junction, and phi x is the total phase here between these 2 points. So think about flux when if you phase you are not used to the phase yet, or since voltage cannot apply. So we can do that. So this device, I didn't tell you, but we can call it AC squid, RF squid, because it's only RF. It's not you have no DC voltage. In electronics, you will call that a Schmidt trigger. You are going to see why if you are used to electronic. And in digital electronic, we call it a DC to SFQ converter. It's because when you apply a DC value or slow varying quantity, you will get a pulse, a very fast pulse. So SFQ, single flux quantum. So when you draw this curve of the external phase versus phase, you see that if the inductance is slow, you have a monotonous curve. But the good thing is that if you increase the inductance, you see sometimes you have this curve. But when you increase the current, external current, it means you increase the phase. In fact, you cannot go like that. You will just follow this, right? So you have jumps here, very fast jumps. The phase of the junction switches very fast. And if you go to the detail, and when you come back, it's the same, right? But it doesn't switch at the same place. So you can calculate when these fluxons appear, when they don't appear. You have a parameter lambda, which is connected. You recognize beta L that we use for squids, the same parameter. It means this product of inductance by current. Basically, it's the size of the loop, and it tells you how many flux you can put inside. And also, as for squids, we want to have small loops to have just one flux, or 0, but not 5 or 10. Otherwise, too complicated to manage. And you can calculate the range for which it will work properly for lambda. So it's usually in this part between 1 and 4.6, if I remember well. Between 1, there is no pulse, and after 4.6, you can have several pulses, so you don't want that. And what happens? What happens when you do that? Before I finish, is that when you apply the current, it goes in these two branches because you have an inductance, Josephson inductance, and finally there is no flux because the current managed it to have a 0 flux because of fluxoid quantization. So you see you have a magnetic field like that here, magnetic field like that here, globally it's 0. But when you have this pulse which appears, what happens is that when you increase the current slowly, all of a sudden it's not possible this case is not possible because there is too much current here. Too much current and the junction higher than IC. So something happens. And this phase of the junction, it will do a 2-pi turn. Then the current will turn the other way, in fact. And after the process, after the pulse is emitted. So basically here you have a constant current in this loop now. You have a flux which is stored in the loop. And this is this one which this one logic information which is stored here. But in the same time, since you had a fast change of phase, you have a fast change of voltage, you have a pulse, and this pulse will propagate at the speed of light. So it's a bit like when a plane takes off, you have a conservation of the rotational for energy reasons and momentum reasons. And then you have, let's say, a fluxon and an anti-fluxon. So behind the plane, when you take off, you have a small vortex of wind to compensate for the change of orientation. And it's the same here. You have a vortex here and one and another one going at the speed of light. So here now you are able to fabricate one single pulse, right? And you can fabricate it very simply. You just need to choose when, at what speed you increase the current. So when you are here and you just put the current here, you will have a switch. And that's about the principle. So you can simulate all this. Now you can, I will not go to the detail, you can use SPICE generator, you can make a netlist, and you can calculate these pulses, you can check the current in the loops, is in the inductance. I'm not going to go to all this. It's not so complicated. And I will just show you how you can use it after. It's another example to show how you can understand these pulses. When you increase the current, you see that the pulse of voltage appears here, and there is a negative one when you go back to 0, right? And in the end, you are in the same process when the loop is too small. But when the loop is big enough to store a pulse, you see that you have a pulse, and after in the loop, in this inductance, you have a current, which is constant, which corresponds to this flux, this stored flux, right? When you go back to 0, your current is still there, right? And then you have a negative current on the junction. It means you have a flux like that. So you have your flux. Now you can use it to make cells. I think the animation will not work on this video, but okay. You have 3 Josephson junction with our shunts. You have an inductance. This is a loop here, and when you put so you have a bias here. So this bias is there just to bias the junction just below IC, right? So it's not there is no voltage. When the pulse arrives, fabricated by the device I showed you before, this single flux SFQ DC converter or DC SFQ converter, there will be an additional current coming here, which will add up with this one. The 2 currents are higher than IC. Then this junction is going to switch, and then you have a pulse coming here, which will be emitted. It will be how to say. This junction will switch, but not this one, because this one is not biased. So you will have your pulse as a circular current. Your one is stored here, and when you want to take it back, your information, you put a clock, you put a pulse here. You will have an additional current which adds to the current running here. This junction will have a current higher than IC. Then it will switch as well, and your pulse will continue. So you have a way to store a flux to make it go with a clock, and you can do all kind of digital things. So I'm not going to go to all the detail. After, you can do very complex circuits, and you can fabricate all kind of cells to do AND gates, OR gates, NOT gates, everything. And it looks like that if you do the drawing. It's a bit when you are used to it, you understand exactly what this cell is, but otherwise you see the junction with the resistance in parallel, you see the inductances, you see the bias lines to bring the bias to bias the junctions, and you see input and output signals. And the clock, I think the clock is this path here for this cell. I think I'll nearly stop here, so you can simulate how it happens. You can see the input, you can see all the voltage pulses, and so you can do all kind of optics. You can calculate the margins. It means if you change a parameter, will it still work? You want a circuit which works when it's fabricated, right? So you need to have some range of parameters, so you manage it and you calculate this margin to be sure, even if there is slight difference in fabrication, it will still work. You can calculate the yield. It means if you have you have some spread of parameters, you can calculate that if the spread is less than 10%, 70% of your chips will still work. If you have a large spread of 40%, then you have only 5% of chips working. It means you need to measure 20 to have one working for a simple cell. So you can calculate all this to see if you can do simulations and get the right circuit. I show again this fabrication with all the layers. You have the resistance here, I told you, with all the layers. So it's really microelectronic process. And okay, so the detail of the technology. This is the Fluxonics foundry in Germany at our PhD, where you can have a library of parameters. So if you want to fabricate circuit, you can ask us, and we can design them. We can fabricate, or you can design, and they can fabricate. You have a library of parameters, and everything is given. You know, tolerances. Then you can have your and you can do other cells. This is a toggle flip-flop cell. And I'm going to show you, okay, with the properties, margin, yields again, And when it's fabricated, looks like that. Picture is not very good, but you can see how circuit looks. Okay, you can do measurements, of course, to verify that everything is fine, to compare with what you expect. Of course, you cannot measure the pulse, but you can make a cell which which has a non-zero value when you have a pulse, input pulse, and which goes back to zero when you have another pulse. So when you have two pulses, here it's zero before, here it's a 1, here it's 0. So when you measure this signal, which you can see on an oscilloscope, what is important is not the value here, it is the time when you change, because then you know you have a pulse, and you can check if it's okay or not. I wanted to show you, maybe I will see if I can find directly the number of this slide. It's here, so you can have, we have this cell library if you want to do some circuit, DCSFQ to generate single flux, to transmit them, to split in two parts, to merge them, to get a DC voltage at the output, and flip-flop, some DFF, delay flip-flop, and all kind of non-destructive readout things to make multiplexers. All these cells have been designed and they work. They can be used to make all kind of circuits. We measure the maximum frequency, typically 40 gigahertz of clock for this simple circuit. So it works reasonably with the technology. Many applications that you can do, right? In different fields, science, security, intelligence, applications in telecommunication as well, analog to digital converters. So there is a big range. Here is an example of analog digital converters made by Hi-Press in the US, when you have nearly 5,000 junctions, 5 to 10. Okay, some floating point units made in Japan, where you can see different parts of these circuits, and 79, I think. And this is even an integrated system, more than 10 years old already. When you have the compressor to cool the cooler at 4 Kelvin, inside you have the chip, probably about here, and you have the electronics to control it. Very simple room temperature electronic. Everything is in at 4K, in fact. And I think that's about it. So I just like to, this slide has a bit of difficulty to come, but it's the last one. Yes, I'd like to thank you for your attention. This is a picture that I took in France 7 years ago, where you can see a phase jump, right, with a Cooper pair passing. I've been lucky to see, not everyone can see it. I'd like to give credit also to this presentation to Paul Zeidel, who really helped and who couldn't do this short course, part of the short course today, and to some of my former students who provided also some content. And yeah, I hope it will give you some hint. If you have questions, don't hesitate. And also, I'd like to say that probably at some point I will cut this presentation in small parts and put them on a YouTube chain. So if you're interested in YouTube channel, so if you're interested, you just send me an email, and when it's ready, you will be able to get some of this content online. Thank you.